Hello everyone. I am starting a new series where we'll understand the fundamentals of generative AI. I know that there are already many videos about AI, but if you're new to this field and want to learn AI, the first thing you should do is to understand the basics. Because if your foundation is not clear, then all the different AI topics you see on your YouTube or across the different social media can become confusing for you. So in this part, we are going to start from the big picture. We'll understand what generative AI actually is, how is it different from the traditional AI, then we'll talk about the foundational models like LLM, SLM, and how to choose which one is the right model for you. So by the end of the video, you should have a clear mental map of generative AI. And you should be able to understand the common terms people use every day. And more importantly, you will understand what those terms mean in the real project. So let's start. First, let's understand what generative AI means. So generative AI is a type of the artificial intelligence that can create new content. Now, this content can be your text, your code, images, audio, video, or even the structured data. For example, when you ask ChatGPT to write an email, it generates new text for you. And when you ask any other tool to create an AI image for a specific city or a futuristic city, it generates a new image. Same way, when you ask the GitHub Copilot to write a Python function, it generates the code. So the important point is generative AI is not simply searching for the existing answers or copying it. It learns pattern from a huge amount of data, and then based on your request, it generates a new output. Now, think about a normal search engine. You search for something, it gives you links. Then you open those links and read the information yourself. But with generative AI, you ask a question and the model directly generates an answer for you. And this is why generative AI feels very much different from the traditional software. So you're not only clicking the buttons, you are communicating your intent. You are telling the system what you want, and the model is generating the response based on that intent itself. But one thing to clarify here is generative AI is not a magic. It works based on the patterns, probability, training data, and the context you provide. So whenever it writes an answer, it is predicting what output makes the most sense based on what it has learned and what you have asked. Now, a simple way to remember this is generative AI creates content from the learned pattern. Now, many people get confused between AI, machine learning, deep learning, and generative AI. So let's make this very simple. AI is the biggest term. So artificial intelligence means building system that can perform the tasks that normally need human intelligence. For example, understanding the language or recognizing the image, making the decision or planning or solving problems. Now, inside that AI, we have machine learning. So machine learning means the system learns from the data instead of the humans writing every rule manually. For example, a fraud detection system can look at the past transaction and learn which patterns look suspicious. You do not manually write every possible fraud rule. The model learns from data. Now, inside the machine learning, we have deep learning. And in the deep learning, it uses the neural network with many layers. Now, you would be thinking, what is the neural network now? So basically, a neural network is a system that has multiple connected layers which uses maths and the algorithm to learn the patterns from your examples. Now, it keeps adjusting itself during the training until it is better at predicting and recognizing the correct output. So these deep learning models are very powerful for complex data like text, images, and audio. For example, image recognition, speech recognition, and modern language models use the deep learning. So now, if I'll talk about generative AI, it's a special area of AI that focuses on creating the new content. And many modern generative AI systems are built using the deep learning, especially the transformer based model. So a simple way to remember that is AI is a broad term or broad field. Machine learning learns from data. Deep learning uses the large neural network. Generative AI creates the content. Let's take a simple email example. If a system detects whether an email is a spam or not, that is machine learning. And if a system generates a reply to that email, that is generative AI. So the output type is very important. Now let's understand about the predictive AI and generative AI. So predictive AI is mainly used to predict what may happen. For example, it can predict the sales demand or equipment failure. It can also predict whether a transaction is fraud or not. Now, the output from the predictive AI is usually a score, a class, label, or the number. For example, it may say the customer has a 80% chances of leaving, and that is predictive AI. Now, if I'll talk about the generative AI, so it can take that information and create something useful from it. For example, it can write a professional retention email for that customer. It can explain why the customer may leave. It can also suggest the next best actions for the support team. So predictive AI tells you what may happen. Generative AI helps you explain it, communicate it, and act on it. And if you are thinking that predictive AI is old school or useless, now it's still very important. But generative AI adds a new layer where the system can understand the language, create the content, and assist the humans in a more natural way. Now, generative AI did not suddenly appear one day. It is the result of the many years of progress in AI. So, in the early days, AI were mostly the rule based. That means the human had to define the clear rules. For example, if this condition happens, then do this. This worked for the simple use cases, but it wasn't flexible enough. Then the machine learning became popular. Instead of writing every rule manually, we started giving the data to the system, and the model learned patterns from that data. And after that, deep learning made AI more powerful. So the neural network started performing very well with images, speech, and the text. And then came a very important moment in the AI history. In 2017, the transformer architecture was introduced in a famous paper called as Attention is All You Need. Now, this changed everything for the modern generative AI. Transformer made it easier to train the large models on the massive text data. They also helped models understand the relationship between the words across long text. And don't worry, we'll cover the transformer architecture later in the video series. So after that, large pre-trained models became common. Then instruction tuning made models easier to use. Instead of only predicting text, they became better at following the human instruction. Then chat interfaces made them popular for the normal user. People don't need to understand the machine learning to use them. They could simply type a question and get a useful answer. And now we are in the era of multimodal AI, agents, and the reasoning models. So the model can work with text, images, audio, and the videos. They can also use the tools, connect to the data, and can complete multi-step tasks. So the evolution looks like this: rule-based system, then machine learning, then deep learning, then transformers, then foundation models like ChatGPT, and now agents and the multimodal AI. Now let's understand the foundation models. A foundation model is a large AI model trained on the broad data, so it can be adapted to many different tasks. It is also called as the foundation model because many applications can be built on top of it. Think of it as a powerful base engine. The same engine can be used in the different vehicles if you connect the right body, control, and the workflow. Similarly, one foundation model can support summarization, translation, code generation, question answer, and the chatbot experience. So you do not always build a separate model from scratch for every different task. You start with a strong base model, then you adapt it using the prompts, RAG, fine tuning, or the different tools. For example, models like OpenAI GPT models or Google Gemini, Anthropic Claude, and Microsoft Phi are examples of the foundation model. So these models can be used as the starting point for the many AI applications. So basically, one foundation model can help with writing an email, summarizing a document, and generating code. It can also answer the customer questions or classify the support ticket if the right prompt and the data are provided. Now, foundation models are not only for text, they can also work with images, audio, video, and the multiple data types together. So, the large language model or LLM are one type of foundational model that focuses mainly on the language task like writing, summarizing, reasoning, and answering the questions. Now, if I'll talk about the small language model or SLM, they are also the language models, but they are designed to be lighter, faster, and more efficient for specific use cases. So, when someone says foundation model, think broader. It can include the language, vision, audio, or multimodal models. So, when someone says LLM or SLM, think language focused models with different size and the capabilities. So this distinction is important because generative AI is not only about the chatbots, it is also about creating and understanding the content across the different formats. Now let's talk about the large language model or the LLM. So an LLM is a model trained to understand and generate the language. It learns from a very large amount of the text and code. So during the training, it learns pattern in the language. At a basic level, an LLM predicts the next token. And now, what is token? So, token can be a word, part of a word, or even the pronunciation. So, this sounds simple, but when the model is trained at a very large scale, it becomes extremely powerful. It can answer questions, explain topics, write contents, or generate the code for you. Now, here is the real example you can relate to. Whenever a new model is released, you may see the names or the descriptions like 7B, 13B, or 70B model. Now, B means billion parameters. Parameters are internal values that the model learned during the training. So you can think of the parameters like the knowledge knobs inside the model itself. And during the training, the model adjusts these values so it can better understand the patterns in the language. So when someone says a model has 7B parameters, it means it has around 7 billion learned values. And same, if someone says 70B, it means 70 billion learned values. And one thing to note here, bigger is not always better for every use case. A very large model can give better reasoning, but it can be also slower or more expensive. But a smaller model can be faster and the cheaper option here. Let's take a simple example. If you're asking an AI model to write a complex migration plan for an enterprise application, then you have to select a stronger model. But if you're only classifying whether a ticket is about the password reset or a network access, a smaller model can do same thing very easily. Now, this is the knowledge gap many people have. They see 7B, 70B, or 400B and think bigger always means better. But in the real projects, we choose the model based on the task, accuracy, latency, cost, and even the security. So LLM are powerful, but model choice matters a lot. Now let's talk about the SLM or the small language models. So an SLM is a smaller language model designed to be faster, cheaper, and easier to run. So it's usually the fewer parameters than the large frontier model. For example, Microsoft 5 family is a good example of small language models. There are also many other smaller models in the market from different providers and even the open model communities. Now, an important question here is, why do SLM matter? And the answer is because not every task needs the most powerful model. Let's say you are building a help desk system. The first step is to understand the ticket type. Is it a password reset? Or is it a network issue? Or is it a billing issue? For this type of focused classification, a small model can work very well. You don't need to send every request to the biggest model. Another example is the mobile or the edge AI. If an AI needs to run on a device, a small model is more practical. It can be faster, cheaper, and more private because some processing can happen closer to the user. Think of it like a vehicle. You don't use a truck to deliver the small parcel. In the same way, you don't use the biggest AI model for every small task. So basically, SLM are very useful for classification, extraction, simple summarization, and routing. And LLM are useful when you need the deeper reasoning, complex generation, or broader understanding. So the key message is simple: use the right model for the right job. Now let's discuss an important topic. Understand the model openness. Now many people say is the open source model, but in AI we need to be careful with the words. There are three useful categories. One is open source model, then open weight models and proprietary models. So an open source model should give enough rights to inspect, use, modify, and share under the open terms. An open weight model may allow you to download the model weights, but the license may still have restrictions. And if I'll talk about the proprietary model, it's controlled by the provider and is commonly accessed through APIs or the managed platform. Now, the industry often mixes these words together, so it's good to understand the difference. For example, true open source models are like Pythia or Olmo, where the openness is major focus. For open weight models, examples include the Meta Llama, Google Gemma, or Microsoft Phi, where the model weights are available but the license terms may still apply. And the proprietary models, which includes the OpenAI GPT, Anthropic Claude, or Google Gemini, which are used through managed services or the APIs. So if you use a model through an API, you do not manage the model infrastructure yourself. That is easy to start with. But if you host an open source model or open weight model yourself, you get more control. You may get better privacy and customization, but you also become responsible for hosting, scaling, monitoring, securing it. So the decision is not emotional. It's not simply open model is good and closed model is bad. It depends on your use case. If you need faster development and the enterprise support, a managed proprietary model may be better. If you need the full control, data sovereignty, or the offline deployment, an open source or self-hosted model may be better. For example, a bank prefers self-hosting for some sensitive workload, but for a general productivity assistant, they may use a managed model API. Now, important point to understand here is every downloadable model is not automatically open source. Some are open weight, some are open source, some are proprietary. Now, this distribution is important for the architects, developers, and the enterprise teams. Now, the one which we are going to discuss is one of the most important topic in the real generative AI projects, model selection, which means choosing the right model for the right task. Another one is the model routing, which means automatically sending the request to the best model based on your task. So let's first talk about the model selection. Suppose you are building an AI assistant. Once the user asks, summarize this short email. Another user asks, analyze the 100-page contract and find the legal risk. Now, these are different tasks. So, one model may not be the best choice for everything. For summarizing a short email, a smaller or the cheaper model may be enough. But for legal risk analysis, you may need a stronger reasoning model. And same goes with the image analysis or the voice conversation. So, the model selection is about matching the model to your job. You should consider accuracy, speed, cost, context windows, multi-model support, tool calling, and different compliances. Now, a good practical approach in this case will be first, define the task. Second, define what good output looks like. Third, test the multiple models using the real prompts and the real data. The next one is choose the model that meets the accuracy target and then optimize for the cost and latency. Now let's talk about the model routing, which takes one step further. Instead of manually choosing one model for everything, a router can decide which model should handle a specific request. For example, a simple request goes into a small model. A complex reasoning request goes to a stronger model, an image goes to vision model, and same if it's a coding request goes to the coding model. Now, this is powerful because it improves the cost and the performance. You're not wasting your most expensive model on every small question. So, a simple way to explain the model routing is this. Imagine a hospital reception desk. If you have a small issue, then you send to the general doctor or GP. If you have a serious issue, they send you to the specialist. And same way, if you need X-ray to be done, then imaging department. That's how the model routing works. It sends the request to the right model. And this is important for the enterprise AI because cost can grow very fast. If every request goes to the largest model, the solution may become expensive. But if you use the model routing, you can balance the quality, speed, and the cost. So the final lesson here is do not choose the model based only on the popularity. choose them based on the work they need to do. And wherever possible, use the model routing to send each request to the most suitable model. Okay, to summarize this video, in the first part, we started with the big picture. And this is the foundation you need before going into the tokens, transformer, embedding, and the RAG. Now in the next part, we'll go deeper how these models actually work. We'll understand the tokens, the different context window, inference, latency. And once you understand everything, then we'll move on to the further topics like RAG, fine tuning, so that these advanced topics will become easier for you to understand. So that's all I wanted to show in this video. So now in the second part, we are going one level deeper. But before we talk about the model training or transformers, agents, or production architecture, we need to understand one very important thing. How does information actually go into AI systems? So when we write a prompt, does the model read it like a human? So when we upload a document, does the model see the pages? So these questions are very important, because if you understand this layer properly, then the topics like the context window, RAG, vector search will become much easier. So in this video, we're going to understand tokens, tokenization, embeddings, vector representation, and semantic similarity. And I will explain each concept in a very simple way. And I'll give you a real example too, so that it becomes more relatable to you. Now, let's start with tokens and tokenization. So, when we humans read the text, we read words, sentences, and paragraphs. For example, if I write Azure is powerful, you and I read this as one single sentence. But an AI does not directly read the text exactly like a human. So, before the model can process the text is broken into the smaller pieces, and these smaller pieces are called as the tokens. Now, a token can be a full word or a part of a word or a number, symbol, even the punctuation. So the process of breaking the text into the model is called as the tokenization. So now if I'll explain in the simple words, tokens are the small pieces of text that the model can process. And the tokenization is the process of breaking the text into those pieces. So let's take a simple example. If I write, I love cloud computing, a human sees four words, but the model may break the sentence into the tokens, like I could be separate, then love, then cloud and computing. And sometimes a word may become one token, but in other cases, it can be, if it's a longer or uncommon word, it can be split into the multiple tokens also. Now, this depends on the tokenizer used by the model. So you may ask, why does this matter? And this matters because AI model do not calculate the cost based on the pages. So they work with tokens. So input is measured with the token, output is also measured in token, same the context window is measured in token. So if I'll talk about the pricing, it's usually based on the tokens. And similar way, if there is a latency, that is also affected by the token. So if you're building an AI solution, tokens directly impact cost, speed, and the design. Now, let's take a real example. Suppose you're using an AI model through an API. You send a small prompt like write an email for a leave request. This may use only the small number of tokens. But if you send a 100-page policy document with the same question, the model needs to process the thousands of tokens, and which means, of course, more cost. And not only the cost, it means more delay also, because it has to process the whole document. And if the document is too large, it may exceed the model context window even. So this is why we do not always send the full document to the model. Now in the real projects, we usually break the document into chunks. Then we retrieve only the relevant part and we send that part to the model. And this is the foundation of the RAG, which we'll cover later in the series. Okay, let's make it more relatable. Imagine you are sending a parcel. Now, so the courier company doesn't only care about the box, they care about the weight, how heavy is it. And it's not that the big box can be heavy, the small box can be heavy too. So same way, AI does not care about the document is 10 pages or the 100 pages. It cares about how many tokens it needs to process. And one more important point is that the different language model can use the different token counts. Same way, if you are using English or any other language, then the token count can also differ. So if you're using a multilingual chatbot, tokenization can affect your cost. So this doesn't impact when you're using a service, but in the real enterprise application, this matter. So remember that simple line. The model does not see the pages, the model sees the token. And based on the token, you decide how you have to use in your AI solution. Now, let's move on to the embedding. So embedding is one of the most important ideas in the modern AI. So it's a numerical representation of meaning. In simple words, embedding converts text into numbers so machine can compare the meaning. Now, humans can read a sentence and understand the intent. Machine needs a mathematical way to compare that information. Embedding solves that problem. Let's take a simple example. The first sentence is, how do I reset my password? And now take a second sentence, I forgot my login password. Now these two sentences use different words, but the meaning is very similar. So a good embedding model will convert both sentences into numbers that are close to each other. And if we'll take another example, what is the weather today? Now this sentence has completely different meaning. So the embedding should be far away from the password related sentences. Now that is the basic idea. Embeddings helps machine understand that two different sentences can have the similar meaning. And this is important because users do not always use the same word that exists inside a document. Because they ask the questions naturally. The system will need to find the right content and imagine every sentence become a point in the map. So the sentences with the similar meaning are closer together. So sentences with a different meaning are far away. So the question on how do I reset my password and the question on how I forgot my password will be near to each other on the meaning map. And the another question, what is the weather today, will be the different area of the map. So this map is not a physical map, it's a mathematical space. So embeddings are like the coordinates on your map. Now, where do we use the embeddings? So we use them in the AI search, RAG, recommendation system, or to find the duplicate records. So in simple words, embedding are used whenever we want machines to compare the meaning. Let's take a practical example. Suppose a company has thousands of internal documents. They may have HR policy document, IT support guides, or finance process document. So when a user asks, how can I reset my laptop password? The system needs to find the right IT document. If we only find the keyword search, it may look for the exact word like reset, laptop, and password. But what if the document says the device credential recovery process? The words are completely different, but the meaning is related. So embedding can help find that document because they compare the meaning, not only the exact words. And this is why embeddings are very important in the AI based search. But one important point is that the embeddings are not normally the final answer. So it can help find the related information, but then we have to use the LLM from that information to generate the final answer. So you can think of the embedding as a smart librarian. The librarian finds the right book and the right page, but the LLM reads the page, explains the answer in the simple language. Now let's move on to vector representation. So a vector is simply a list of the numbers. So in AI, vectors are used to represent text, images, audio, and other information in a machine-friendly format. So when you create an embedding for a sentence, the output is usually a vector. For example, a sentence may become a list of the hundreds or thousands of the number. We cannot look at those numbers and understand the meaning, but a machine can compare those numbers very quickly. Let's take an easy example. Suppose we have two phrases. The first one is the annual leave policy, the second one is the vacation entitlement. Now, these are different words, but in the meaning they are related. A good embedding model will create a vector representation that are close to each other. And this helps the system retrieve the right policy even when the users doesn't use the exact word from the document. So a vector is like a machine readable identity for a piece of content. And the content may be a sentence, an image, or a code snippet. So the vector helps the system compare it with the other things. And this is very important because the vectors are not only the text, images, and audio, but the products are also the vectors. So this is why the vector search is used in many areas. And the connection is simple. Embedding create the vectors, vector represent the meaning or the features, and then vector search compares those vectors. Now let's move to semantic similarity. Now, this means that comparing the meaning, not just the exact word. And this is one of the biggest differences between the traditional search and the modern AI powered search. So, traditional search looks for the matching words, but in the semantic search looks for the related meaning. Let's take a simple example. A user asks, "Can I work from home?" The company policy document may not say work from home. It may say remote work policy. So there are chances that traditional keyword search will miss it, but the semantic search can understand that work from home and the remote work are related. And this is the semantic similarity. The words are different, but the meaning is similar. So semantic similarity helps the system connect them. So at a high level, the system converts the text into embedding. Then it compares the vectors. So if the two vectors are very close, then the meaning is likely similar. And one common method used for comparison is cosine similarity. You don't need to understand the maths in detail for now. Just remember that cosine similarity helps compare those two vectors are in the same direction. And this is where the people sometimes get confused. Semantic similarity is powerful, but it is not perfect. It can still retrieve the wrong content. Now, this can happen when the question is unclear or when the document chunks are poor or when two topics sound very similar. So if the system is not designed properly, it may retrieve the wrong one. And that is why the production search system often use the hybrid search and re-ranking. So hybrid search combines the keyword search and the vector search, and the re-ranking takes the results and sort them again based on the relevance. So we'll cover these topics later in the RAG section, but for now, just remember that semantic similarity helps find the meaning based matches, but in the production, we normally combine it with the other techniques to improve the accuracy. So if every user question sends the full HR policy to the LLM, cost will be very high. If the policy is large, response time will also be high. Instead, we use the embedding and the semantic search to find only the most relevant chunks. Then we send those chunks to the LLM, which reduces the cost, improves the speed, and improves the answer quality because the model receives focused information. So let's quickly summarize what we have learned. Tokens are the small pieces of text that the model processes. Then tokenization is the process of breaking the text into those pieces. Now tokens affect the cost, context window, speed, and the limit. Then comes the embedding. So embedding converts text or the other data into numerical values or the meanings. Now vectors are the list of the numbers that store that representation. Semantic similarity compares the meaning using those vectors. And together, these concepts power AI search, RAG, recommendation, and the intelligence agents. So, if someone asks how AI chatbot find the right answer from the private document, now you know the basic flow. It does not magically read everything like a human. It tokenizes the text, convert meaning into embeddings, store the meaning as the vectors, compare the vectors using the semantic similarity, and then the LLM uses the retrieve content to generate the final response. So in the next video, we'll move into the next layer. We'll understand how models are built and trained. We'll cover the model parameters and the model size. And once you understand that part, you will know how these models are created and improved because we use them in the application. So that's all for this video. Now in this third part, we are going one level deeper. Today we'll understand how these models are actually built and trained. Many people use models like ChatGPT, Claude, or open models like the Llama or Mistral, but they don't know what is happening behind the scenes. You hear words like parameters, pre-training, fine-tuning, synthetic data, and they feel confusing. So in this video, my goal is simple. I want to explain these concepts in a very practical way. And after watching this, when you hear these terms in AI discussion, documentation, or the YouTube videos, you should immediately understand what they mean and where they fit in the model training journey. So let's start. First, let's understand the model parameters and the model size. So whenever a new model is released, you see the numbers like 7B, 13B, 70B, or even the bigger numbers. Many people see these numbers and think, what does this actually mean? So here B means billion And if a model has 7B, it means the model has around 7 billion parameters. If it's 70B, it means 70 billion parameters. Now, what are parameters? So the parameters are the internal values learned by the model during the training. And you can think of the parameters like the tiny knowledge settings inside the model. So during the training, the model keep adjusting these values so that it can better predict and understand and generate the language. Let's take a simple example. Imagine you are learning to drive a car. In the beginning, you do not know how much pressure to apply on the brakes, when to turn the steering, or how fast to accelerate. But after practice, your brain learns many small patterns. You do not remember each rule separately. Your brain adjusts based on the experience. Model parameters are similar in the concepts. So during the training, the model learns small patterns from the data. These patterns are stored in the form of the parameters. Now, a bigger model usually has more capacity to learn complex patterns. So, a 70B model can generally store and represent more complex relationships than a 7B model. But the bigger is not always the better for every use case. For example, if you only want to classify the support tickets into categories like the password reset, network issue, or the billing queries, a smaller model may be enough. But if you want to analyze a long legal document, write complex code, or prepare a cloud migration strategy, then a larger or a more capable model may give you better result. So the model size matters, but it is not the only thing that matters. Training data quality, model architecture, alignment, context window, latency, and the cost also matters. So a simple way to remember this is parameters are like the model learned internal values or the settings. More parameters can give more capability, but only when the model is trained well and used for the right task. Now let's talk about the pre-training. So pre-training is the first major training stage for a foundation model. So in the pre-training, the model is trained on a very large amount of data. And this can include the books, websites, documentation, code, or articles, depending on the model provider and the data policy. Now, the model is not trained like a human student reading a chapter or answering each question. It is trained typically to predict a task. At a very basic, the model learns to predict the next token, and a token can be a word, part of the word, or a punctuation. For example, if the training sentence is the capital of Australia is Canberra, the model may see the capital of Australia is and it tries to predict the next token. The correct answer is Canberra. Now imagine this happening not once but billions or trillions of times across a huge amount of data. So slowly the model starts learning the grammar, facts, writing patterns, coding patterns, or the relationship between the ideas. And this is why the pre-trained model have broad general knowledge. But here is the important point. A pre-trained model is not automatically a helpful assistant. After pre-training, the model has learned the language pattern, but it may not properly follow the instructions. It may complete text instead of answering, or may continue your sentence instead of helping you. So pre-training gives the model general knowledge, but not necessarily the good behavior. A simple example. If you write explain the cloud computing to a beginner, a raw pre-trained model may simply continue with the similar text from training data. But an assistant model will understand that you are asking for an explanation. The assistant behavior comes from the next stages. Now, let's talk about the instruction tuning. So, instruction tuning means teaching the model to follow the human instructions. So in this stage, the model is trained on the examples where there is an instruction and a good response. For example, if there is an instruction like explain the virtual network in simple words, and there are different responses like Azure Virtual Network is a private network in Azure where your cloud resources can communicate securely, and another example where other instructions are provided. There are many examples like this. By seeing these examples, the model learns how to respond to the user request. And this is why modern AI assistants are useful. They do not only predict text, they understand the task format. If you ask them to summarize, they summarize. If you ask them to write an email, they write an email for you. Think of pre-training like giving someone broad education. And instruction tuning is like giving that person customer service training. They already know many things, but now they learn how to respond properly when someone asks for help. So now let's talk about the alignment. Alignment means making the model more helpful, safe, and better match with the human expectation. So a model can generate text, but that doesn't mean that each answer is safe, correct, and useful. So the alignment is used to improve the model behavior. For example, if someone asks a dangerous question, the model should not provide the harmful instructions. Same way, if someone asks a medical or a legal question, the model should be very careful and not act like a certified professional. So the alignment is about shaping the model's behavior. Now, one of the well-known techniques used for alignment is RLHF. Here, RLHF stands for Reinforcement Learning from Human Feedback. Let's make this simple. The model gives multiple responses to the same question. The human reviewers compare those responses and say which one is better. For example, a user asks explain the Kubernetes to a beginner. There are response A, which is too technical, response B, which is clear and simple. Now the human reviewers may prefer response B. So over many examples, the model learns what kind of responses humans prefer. So RLHF helps the model become more helpful and more natural. Now another important technique is DPO, and DPO stands for Direct Performance Optimization. And DPO also uses preferred and rejected responses. But it is simpler than older RLHF approach because it directly trains the model to prefer the better answer. Let's take this example. So the question is write a short leave request email, and the preferred answer is clear, polite, and short, and the rejected answer is too long, rude, or confusing. So with DPO, the model learns to produce the answer closer to the preferred style. You do not need to provide the maths behind the RLHF or DPO at this stage. Just remember this. RLHF, DPO are the methods used to improve the model behavior based on the human or preference based feedback. Now let's talk about the fine tuning. So fine tuning means taking an existing pre-trained model and training it further on a specified dataset or task. You do not have to start from zero. You start from a model that already understands language. Then you customize it. For example, let's say you're building a support assistant for an insurance company. The base model already knows the general language, but it may not know about your company's response style, policy wording, or the ticket categories. So you can fine tune the model using the examples from your own support tickets. For example, the customer says they need help updating the address, and then there is output that classify as profile update and generate a profile response. So after the fine tuning, the model becomes better at specific tasks. Now, one important question: when should you use the fine tuning? So fine tuning is useful when you need a model to behave consistently for a specific task. It is also useful when you have too many good examples and the task is stable. For example, classifying a support ticket or extracting fields from a standard document or writing response in a specific company tone. But fine tuning is not always the right answer. If your requirement is to answer the questions from the changing document like HR policies or product manuals, then RAG may be better, because RAG means the model retrieves the latest information from the documents before answering. Now, we are going to cover the RAG in the later videos. So just understand the simple rule. Use the fine tuning to teach the behavior of the pattern. Use the RAG to provide the latest knowledge. Now let's understand LoRa, QLoRa, or PEFT. Now these words sounds very technical, but the idea is very simple. Full fine tuning means updating many or all the parameters of the model. This can be expensive and heavy, but in many cases you don't need to update the full model. So LoRa stands for low rank adaptation. So it's a technique where we keep the main model mostly frozen and train small extra adapter layers. Think of it like this. You bought a ready-made suit. Full fine-tuning is like redesigning the whole suit from scratch. Now, LoRa is like making the small adjustment so it fits your body better. The base model stays the same, but the small trainable data or the parts are added to adapt the model for your task. Now, this makes fine-tuning faster, cheaper, and easier. Now, Moving on to QLoRa, we goes one step further. It combines the LoRa with the quantization, so the model can be fine-tuned using less memory. Another is PEFT, which stands for parameter efficient fine-tuning. Now, LoRa and QLoRa are the examples of the PEFT method itself. The main idea is that instead of changing the full model, we change only a small number of trainable parts to make the model better for the specific task. And this is very useful when you want the customization without the cost of the full training. Now, let's talk about the quantization. The quantization means reducing the precision of the model numbers so the model becomes smaller and faster to run. Normally, the model weights may be stored using the high precision number. So the quantization reduces that precision. For example, instead of using a 16-bit number, the model may use the 8-bit or 4-bit numbers. This reduces the memory usage and can make the model faster. Let's take a real life example. Imagine you have a very high resolution photo. The original photo may be of 50 megabytes and you compress it to 5 megabytes. The quality may reduce slightly, but for normal viewing, it still looks fine, right? So the quantization is similar. You reduce the model size while trying to keep the quality acceptable. And this is very useful for running the models on laptop, edge devices, or lower cost services. But there is a trade-off. If you compress the model too much, the quality may drop. So the quantization is about balancing the performance, cost, and quality. Now let's talk about the model distillation. So distillation means training a smaller model to behave like a larger model. And in this case, the larger model is called the teacher model and the smaller model is called the student model. So the larger model generates the high quality output. The student model learns from those outputs. So the goal is to create a smaller model that is faster and cheaper, but still gives strong response for a specific task. Now, the real life example. Imagine a senior architect explains the cloud design patterns to a junior engineer. The junior engineer may not know everything the senior knows, but the common design task, they can learn the right approach. In the model distillation, the large model teaches the smaller model. And this is why some smaller models can perform very well in the specific task. They may not be as strong as the frontier model for everything, but for focused use case, they can be very powerful. Now let's talk about the synthetic data. So synthetic data means data generated artificially, often using the artificial model or AI models. Now, why this is useful? Because the training and the fine tuning needs good example. But many organizations do not have enough labeled data. For example, you may want to train a model to classify the customer complaints into different categories, but you only have 100 examples. You can use a stronger model to generate more examples, like different category, billing issue. So you can generate different synthetic customer message for the billing issues. This gives you more training data, but we need to be careful. Synthetic data must be reviewed and filtered. If the bad data goes into the training, the model can learn the bad behavior. A simple way to remember this is synthetic data is useful, but the quality control is very important. It's like making practice exam for the students. If the practice exam is wrong, the students may learn the wrong things. Now, let's connect all of these stages together. First, the model is pre-trained on a huge amount of data. This gives a broad knowledge and the language capabilities. Then the instruction tuning teaches it how to follow the instructions. Then comes the alignment methods like RLHF and DPO, which make it more helpful, safe, and closer to human expectation. Then fine tuning can customize it for specific tasks. LoRa, QLoRa, or PEFT make fine tuning more efficient. Then quantization makes models smaller, cheaper to run. And distillation helps create smaller models from the larger models. Synthetic data helps create the more training examples when the real data is limited. So when you use an AI assistant, you are not just using one simple algorithm. You are using the result of many training and optimization steps. Okay, let's make this practical with one full example. Imagine you are a company who wants to build an AI assistant for IT support. The base foundation model already knows general language and IT concepts because of the pre-training. Now, instruction tuning helps it to respond like an assistant. Alignment helps it avoid unsafe or incorrect behavior. The company then fine tunes it using the historical support tickets so it understands the ticket categories and response style. LoRa makes it fine tuning cost effective. Quantization can run smaller version of the for the internal use at the lower cost. Distillation can create a smaller model for simple tasks like ticket classification. And synthetic data can help create more examples for rare ticket categories. And in production, the model routing can send simple requests to the smaller model and the complex troubleshooting requests to a stronger model. And this is how these concepts come together in a real project. Now let's quickly discuss a common confusion. People often ask, should I fine tune the model or should I use the RAG? The answer depends on the problem. If you want the model to run a behavior, use fine tuning. If you want the model to answer the latest documents, use RAG. For example, if you want the model to always respond in the company support style, fine tuning can help. But if you want the model to answer based on the latest HR policy document, which changes often, then RAG is better. So in many real projects, you use both. And this is an important point for architects and developers. Do not fine tune a model just because it sounds advanced. Choose it only when it solves the right problem. So in this video, we covered how models are built and trained. In the next video, we will go deeper into how the model understand and generate text. We'll cover context window, inference, latency, streaming, transformers, attention, and something similar. So once you understand that part, topics like RAG, agents, production architecture will become much easier. So that's all I wanted to show in this video. So now we know how text enters an AI system, how it's broken into smaller pieces, and how the meaning can be represented in such a way that the machines can work with. So in this video, we are going one step deeper. We will understand what happens after the input goes inside the model. And this is where the important terms like transformers, attention, context windows, and inference comes in. Now, these words may sound technical at first, but once you understand the flow, they will become much easier. Think of it like this. In the last video, we understood how text is prepared before it reaches the model. In this video, we'll understand what happens inside the model itself. How does the model connect related words? How does it understand? So the goal of this video is simple. By the end, you should have a clear and practical understanding of how the modern language models process text and generate responses. Let's start with transformer architecture. So a transformer is the main architecture behind the many language models or the modern language models. So when people talk about the models like GPT, Claude or Llama, they are mostly talking about the models built using the transformer architecture. And you can think of the transformer as the main engine of the model. So the tokens go inside the engine or into the engine, and then the model passes those tokens through many layers of calculation. So each layer helps model understand the input better, connect related words, and prepare the information needed to generate a useful response. So before the transformers became popular, many language systems used the older approaches like the recurrent neural networks. These systems process the text more sequentially, almost like step by step, and that made them harder to train at a very large scale and less efficient when working with the long text. But the transformer changed this because they allowed the model to look at the different parts of the inputs more flexibly and understand the relationship between the words, even when the words are far apart in the sentence. So let's take a simple example. The server failed because it ran out of memory. So as the humans, we quickly understand the word it refers to the server. We do not need anyone to explain that. But for a model, this relationship has to be calculated. The transformer helps the model work out which tokens are connected to which other tokens. So in this example, it can connect it back to the server, and it can also connect the memory to the reason of the failure. So this connection happens mainly through a mechanism called as attention, which we'll understand later in this video itself. But at a higher level, attention helps the model decide which parts of the input are important for understanding each token. A good real life example is reading an email from a customer. The customer may mention an application at the start of the email and later they mention that it's not responding. So, as a human, you will understand immediately that it means the application. And a transformer helps the model do the similar kind of connection, but through the maths, probabilities, and the learned patterns. Now, this is important to understand. The model is not thinking like the human. It's not reading the human emotions or common sense or real life experience. It is using the patterns learned during the training. Now, during the training, the model sees a huge amount of text and repeatedly learns how the words, tokens, and ideas are usually connected. So, over the time, these learned patterns help the model make useful connections when we give it new prompt. So inside a transformer, the input passes through the many layers. You can think of each layer as a processing block. Now, in each block, the model first uses the attention to understand the relationship between the token. Then it uses another processing step called as feed forward network to refine the information. Now, there are also supporting techniques like residual connections and normalization, which help keep the information stable as it moves through the many layers. So, the model does not understand everything in one single step. The information is refined layer by layer. Uh, the information is refined layer by layer. Early layers may capture the simple patterns like the words and the sentence structure. Middle layer may capture the relationship between the different parts of the text, and the deeper layer may capture more complex meaning, context, and the intent. So by the time the input has passed through many transformer layers, the model has built a much richer representation of the text. And this is also the reason why modern AI models need a lot of compute. So a transformer is not doing one small calculation. It is doing a huge amount of mathematical operations across the tokens, attention, heads, and multi-layers. Now these calculations are mostly matrix based operations and GPUs are very good at running these operations in parallel. So when we hear the large language models need powerful GPUs, high memory, and large compute cluster, this is one of the main reasons. The model has to process many tokens through many layers or multiple layers. And during training, this happens again and again on massive amount of text. Now, modern GPUs and the cloud scale compute made it practical to train and run these large scale or large transformer based models at scale we see today. So when the representation of the text is built, then it can use that representation to predict the next token and generate the response one token at a time. So the simplest way to remember this is the transformer is the engine that helps the modern language models process the tokens, connect related information, understand the context in a machine-based way, and generate text step by step. Now, inside this transformer engine, one of the most important concepts is attention. And attention helps the model work out which tokens are more relevant when it is processing a particular token or generating a response. Let's use the same sentence again. The server failed because it ran out of memory. When the model processes the word it, attention helps it connect to the word back to the server. It also helps the model connect the memory with the reason of the failure. So the attention is not just looking at one word, it's checking the relationship between the different words in the input. Another simple example is this prompt. Summarize the second paragraph and ignore the first paragraph. So in this case, the model should give more importance to the second paragraph and reduce the importance for the first one. Now, attention helps the model focus on the right part of the input based on the task. So a simple way to understand attention is to compare it with reading a document. When someone asks you a question, you do not give full focus to the every line. You naturally focus on the lines that matters. So attention is the model's mathematical way of doing something similar. It helps the model decide what to focus on and what to connect and what information is useful for the next step. Now, there is also a term called as self-attention. So self-attention means tokens inside the same input can look at the other tokens in the same input. And this is important because a word does not always get its full meaning from itself. It often gets the meaning from the words around it. For example, if the sentence says, the application crashed after it reached the high CPU usage, the model needs to connect it back to the application. And self-attention helps the model build these connections across the inputs. It can help with pronouns, grammars, technical context, and even the long instructions inside a document. So in a technical discussion, you may also hear the terms query, key, and value. And for the fundamentals video, we don't need to go deeper into the maths. The idea is simple. The model checks what each token is looking for, compares it with the other token, and then pulls the useful information from the most relevant ones. And that is the basic intuition behind the self-attention. Now let's move on to encoder, decoder, and decoder only models. So the transformer models can be designed in different ways depending on the task. Some models are mainly used to understand the inputs, while others are mainly used to generate text. And this is where the encoder and decoder concept comes in. An encoder reads the input and creates a useful representation of it. And this is helpful with the tasks like classification, embedding, semantic search, and comparing the meaning between the different pieces of text. So a decoder generates the output step by step. This is helpful for the chatbots, text completion, and content generation. So it takes the previous token as context and keeps predicting the next token. An encoder decoder model uses both the parts together. So encoder first understands the input and the decoder then generates the output. And this type of design is useful for the tasks like translation, summarization, and converting one form of text into another. Let's keep it simple. An embedding model usually focuses on understanding the text and convert it into the vectors. So it is closer to encoder style task. A chat model needs to generate text from one token at a time. So it is closer to the decoder style task. And many chat models are decoder only models. They read the conversation as context and then keep generating the tokens until the answer is complete. So when you ask an LLM a question, it does not create the full answer in one step. It predicts one token, then the next token, and continues processing until the response is finished. Now, this token by token generation is one of the key ideas behind the modern language models. Now, let's talk about the context window. So, the context window is the amount of the information the model can look at in one request. It is measured in tokens. It includes the user input, system message, and conversation history. It can also include the retrieved document, search result, or the tool outputs if your application is using RAG or the agents. A large context window means the model can accept more information at one time. And this is useful when you're working with the long documents, large code files, or detailed logs or the longer conversations. For example, if you're asking the model to review an architecture document or analyze the multiple support tickets, a big context window can help because more information can fit into the request. But a large context window is not the same as perfect memory. And this is very important point. Just because a model can accept a large amount of text, it does not mean it always gives or always use every details correctly. So it may miss something, focus on the wrong section, or give more importance to the less relevant information. So a large context can also increase the cost and latency because the model has to process more tokens. A simple way to understand the context window is to think of a work desk. So if your desk is small, you can keep only a few papers in front of you. If your desk is large, you can keep more papers. But if you put too many papers on the desk without organizing them, finding the right information can still become difficult. In the same way, a bigger context window helps, but good structure still matters. You still need clear prompts, clean, retrieve content, and proper document organization. And the context window is like the model's working memory for current requests. It's not everything the model has ever learned. It's only the information the model can see and use right now. Now, let's move on to inference. Training and inference are two different things. Training is the process where the model is created or improved. Inference is the process where we use the trained models to generate an answer. Now, most users interact with the AI during the inference. When you ask ChatGPT a question, you are running inference. And same way, when you ask an enterprise chatbot to answer your company document, you are also running the inference. You are not training the model at that moment. You are using the model that has already been trained. So during the inference, the model receives input tokens, processes them through its layers, and then generates the output tokens. In most large language models or language models, the response is generated one token at a time. The model predicts the next token, adds it to the response, and then uses that updated context to predict the next token again. And this process continues until the answer is complete. So, a simple way to understand this is to think about a chef. Training is like teaching the chef how to cook different dishes. And inference is when you give an order to a trained chef and ask them to prepare the food. So if the order is simple, it may be quick. If the order is complex or has many instructions, it may take longer. In the same way, inference depends on the many practical factors. Model size matters because the large model usually need more compute. Prompt length matters because longer prompt means more tokens to process. Output length also matters because longer answers requires the model to generate more tokens step by step. So inference is not only about getting a good answer, it is also about the speed, cost, latency, and user experience. This is why in real AI application, architects and developers need to think carefully about the model selection, prompt size, response length, and the optimization techniques. Now the next topic is latency and streaming. Latency means how long the system takes to start responding or complete the response. In a generative AI application, latency can come from different places. It can come from the model, the retrieval step, a tool call, a long prompt, or a long answer. Latency matters because users don't like waiting, but the acceptable delay depends on the use cases. If you are summarizing a long report, a few extra seconds may be acceptable. But if you are building a voice assistant or a support chatbot, even a small delay can feel slow and unnatural. And this is where the streaming becomes useful. So streaming means showing the answers while it is being generated instead of waiting for the full response to finish. You have already seen this in many chat applications. The answer starts appearing word by word or token by token, so the user feels like the system is active and working. And streaming may not always reduce the total time needed to generate the full answer, but it improves the user experience. For example, if the full response takes 10 seconds and nothing appears on the screen, the user may think that the application is stuck. But if the first few words appear quickly, the experience feels much better. In production system, we need to balance the speed, quality, and the cost. A small model may respond faster and cost less, but it may not be strong enough for the complex reasoning. A large model can give the better answers, but it may be slow or more expensive. And this is where the model selection and model routing becomes more useful. Simple requests can go to a faster and the cheaper model, while the complex requests can go to a stronger model. And this helps us build the AI application that are not only intelligent, but also the fast, cost effective, and better for the users. Now let's talk about the KV cache and speculative decoding. So these are the inference optimization technique. So I'll keep them simple. When a model generates an answer token by token, it has to keep using the previous context. For every new token, the model needs to know what has already been generated and what was in the original prompt. So if the model has to repeat all the attention calculation from the beginning every time, generation would become much slower. And this is where KV cache helps. KV cache stands for key and value, which are part of the attention mechanism. The simple idea is that the model stores more attention related information from previous token and reuses it while generating the next token. A simple example is solving a long maths problem. If you write down the immediate results, you can reuse them later. If you do not write them down, you may have to calculate the same thing again. So KV cache works in the similar way. It helps the model continue generating more efficiently, especially with the longer prompts or long responses. Now, speculative decoding is another optimization technique. And the idea is that smaller or faster draft models generate a few possible next tokens. And then the larger model checks them. If those draft tokens are acceptable, the larger model can approve them faster. If they are not acceptable, the larger model rejects them and continues generating normally. So, a relatable example is a junior assistant and a senior assistant working together. So, the junior assistant quickly drafts the next few lines of the email. The senior assistant reviews it. If the draft is good, the senior accepts it quickly. If not, the senior rewrites that part. And that is the basic idea behind speculative decoding. In the most normal projects, you do not need to implement the KV cache or speculative decoding yourself. So the cloud platforms and the model serving systems usually handle these optimization behind the scenes. But as an architect or a developer, it is useful to understand these ideas because they explain why the long prompts may be slower, why some models respond faster, and why the inference optimization matters in the production AI system. Now let's connect the full flow together. A user sends a prompt, and that prompt is converted into tokens. Those tokens go into the transformer models. Inside the transformer, the input passes through the multiple layers. Attention helps the model connect the release part of the input, like which word refers to what, which instructions matter more, and which part of the context is useful for the task. After processing the input, the model starts generating the answer. It does this one token at a time. It predicts the next token, adds it to the response, and then continues predicting the next token until the answer is complete. So if the prompt is long, the context window controls how much information the model can consider at one time. If the application uses streaming, the user can see the answer while it's being generated. If the serving system uses KV cache, generations become more efficient because some previous calculations are already reused. And if the speculative decoding is available, the response may be generated faster by using a draft and verify approach. So in this video, we understood the main flow behind how the modern large language models or the language model process text and generate responses. You do not need to become a research scientist to use the generative AI properly. But if you understand these basics, you can design better prompts, better RAG systems, and even the better AI applications or the agents. So in the next video, we'll move into how we work with the model in practice. We'll cover prompt engineering, structured output, and function calling. We'll also discuss the grounding, hallucination, and knowledge cutoff because these topics are very important when building the real world AI application. So that's all for this video. In this video, we are moving from how the model works internally to how we use the model in the real applications. In the previous video, we understood how text goes inside the model, how transformer processes the token, and how inference generates the response token by token. Now we'll take the next step. And this is the part most developers, architects, and AI builders use every day. Because in real projects, we are usually not training a model or foundation model from zero. Most of the time, we are using an existing model and trying to get the best, safest, and the most useful response from it. So in this video, we'll understand how to work with models properly. We'll start with prompt engineering, system prompts, and prompt templates. Then we'll look at the zero shot, one shot, and few shot prompting. After that, we'll discuss the reasoning patterns like chain of thought, react, and reflection. Then we'll move into the structured output, function calling, and tool calling. Because these are really important when we build real AI applications. And finally, we'll cover grounding, hallucination, and knowledge cutoff. Because in the production system, getting an answer is not enough. The answer also needs to be accurate, safe, and based on the right information. So let's start with prompt engineering. So prompt engineering simply means writing clear instructions for a model so that it can produce a better response. So a prompt is not just a question. A good prompt can include the task, the context, expected format, tone, examples, and the rules. The clearer the prompt is, the easier it becomes for the model to understand what we want. Let's take a simple example. If we write a prompt like write something about Azure, the model doesn't know exactly what you need. If the prompt is too broad, the answer might also be too broad. A better prompt will be write a 150 word beginner friendly explanation of the Azure private endpoint for cloud engineers, and use the simple language and include one practical example. Now, the model has a clear task, a clear audience, a clear length, and a clear output style. And because of that, the response will usually be much better. One important point to remember is that the prompt engineering is not about the magic words or the clever tricks. It's about giving the model the clear direction and the right information to work with. So, in modern AI applications, the industry is also moving from only the prompt engineering to the context engineering. And this means we do not only focus on the user prompt, we also think about the system instructions, prompt templates, retrieved documents, tool outputs, and conversation history, memory, and governed rules. And this is important because a production AI application does not work well because of one smart prompt. It works well when the full context is designed properly. Now, the model needs to know its role, the task, the information it can use, the rule it must follow, and the format it should return. So, the prompt engineering is the starting point, but the context engineering is the bigger picture. Now, let's talk about the system prompts and prompt templates. So, a system prompt is a high level instruction that guides the model's behavior. It usually tells the model what role to follow, what rule applies, and what boundary to maintain. And in many chat applications, the system prompt has higher priority than the user prompt. So it is very important in the real applications. For example, imagine you are building an internal HR assistant. The system prompt may say, you are an internal HR assistant, answer only the provided HR based document or HR policy documents. If the answer is not available in the document, say that the information is not available. Keep the response simple and professional. And this type of instruction is useful because it sets the behavior of the assistant before the user even asks a question. And without a clear system prompt, the model may answer using the general HR knowledge from its training. But for an internal HR assistant, that is not what we want. We want the answer based on the company policies, approved documents, and defined rules. Now, if I'll talk about the prompt template, a prompt template is a bit different. So, a prompt template is a reusable structure that contains fixed instructions and placeholder for the dynamic values. For example, the template may include a placeholder for the user question and another placeholder for retrieved context. So, at the runtime, the application fills those placeholders and send the complete prompt to the model. And this is very useful in the enterprise application because we do not want every developer writing prompt in a different style. We want consistent behavior across the application, and we also want to test the prompt, version them, and improve them over the time. So in serious AI projects, prompts should be treated like the application code. They should be stored, reviewed, tested, and version controlled, because even a small prompt change can change how the system behaves. Now let's move to zero shot, one shot, and few shot prompting. And these terms sound technical, but the idea is very simple. Zero shot prompting means you ask the model to complete a task without giving any example. One shot prompting means you give one example. Few shot prompting means you give a few examples. Let's take a support ticket example. A zero shot prompting may say classify the ticket as network, access, billing, or security. The model receives the ticket and tries to classify it based on only the instructions. In one shot prompting, we'll give one example first. For example, if the ticket says I cannot connect to VPN, classify it as network. So now classify another ticket which is my MFA is not working, and that one example helps the model understand the expected pattern. In few shot prompting, we give multiple examples, and this is useful when we want more consistent output because the model can see what a good answer should look like. A simple way to understand this is training a new team member. If you only explain the rule, they may understand it. But if you show one or two examples, they usually understand tasks much faster. So, few shot prompting is helpful when you want a specific style, format, or domain specific classification. For example, if you want the model to classify internal incident categories, giving a few examples can improve the result. But there is a trade off. Examples use tokens. So if you add too many examples, the prompt becomes longer, slower, and more expensive. It can also become harder to maintain. So in production, we normally start simple. First, try zero shot. If the model is not consistent, add one or two examples. And if the task is high volume, stable, and very specific, then fine tuning may be the best option here. Now let's talk about chain of thought, react, and reflection. And these are the patterns used to improve the reasoning and task execution. So we do not need to go deep into the research details here, but we should understand the practical idea. So the chain of thought is a pattern where the model is guided to break the problem into the steps instead of jumping directly into the final answer. So earlier people used the prompts like think step by step to improve the reasoning. And the basic idea is that some problems are easier when they are solved in stages. For example, if you ask the model to troubleshoot why the application is down, it should not immediately give one answer like restart the server. It should first consider possible causes. Is there any network issue? Is the compute resource healthy? Are there any errors in the application logs? Is the database reachable? So after checking these areas, the model can give a more useful answer. But there is an important point. Many reasoning models always do internal reasoning. And also in production system, we usually do not want to expose a long hidden reasoning trace to the user. What we want is a clear final answer, supporting evidence and safe next step. So instead of asking the model to show every thinking step, we ask it to provide a concise explanation, the main reason and the evidence used. Now, react means reasoning and acting. So in this pattern, the model does not only generate an answer, it also uses tools. It can decide what to check, call a tool, observe the result, and then decide the next steps. And let's take a cloud troubleshooting assistant. A user says, my web app is slow. The assistant should not guess. It can first decide to check the application log, then it can call a monitoring tool. After it sees the result, it may check CPU, memory, dependency failure, or the recent deployment changes. Then it can suggest the next action. And this is a React style flow because the model is reasoning and acting in a loop. Now, reflection is another pattern where the system reviews a previous attempt and improves the next attempt. So a simple way to understand it is learning from the mistakes during the task. For example, imagine a senior engineer reviewing a junior engineer's troubleshooting steps. The first attempt may only check CPU. The senior engineer may say, you checked CPU, but you missed memory, application log, and the recent deployment changes. The next attempt becomes better because it uses the feedback. Reflection follows a similar idea. The system looks at what's missing, updates the approach, and tries again with a better response. Now let's move into the structured output, schemas, and the JSON mode. And this is very practical topic because many AI applications do not only need text for humans, they need output that another system can read and use. If the model returns normal free text, it may be fine for a person. But if your application needs to save the result in a database, create a ticket, or update the workflow or call another API, then free text can become hard to process. And this is where the structured output helps. So structured output means asking the model to return the response in a fixed format. JSON mode helps the model return valid JSON. So the schema based structured output goes one step further because it defines required fields, data types, and allowed values. Let's take a support ticket example. Instead of asking the model to summarize the ticket in a normal text, we can ask it to return specific fields like category, priority, and the next action. For example, category could be access, priority could be high, and the next action could be check the role assignment. And this is powerful because now the AI response can be used by the other system. It can create a ServiceNow ticket, update a dashboard, or trigger an automation, or pass data to another API. And for the production system, schema-based output is usually better than only asking the model to return JSON. And if the schema is strict, the application can validate the response and reject anything that does not match. And this reduces the errors and make the automation safer and more reliable. Now let's talk about the function calling and the tool calling. And this is one of the most important concepts in the AI application development. A large model by itself mainly generates text, but when we connect it with the tools, it can become part of a real workflow. So function calling allows the model to request an external action. The model does not directly perform the action by itself, it selects the right tool and provides the required arguments. Then the application executes that tool, gets the result and send it back to the model. And after that, the model can use the result to respond to the user. Let's take a simple example. A user asks, how many virtual machines are running in my subscription? The model should not guess the answer. It should call a tool that checks the Azure subscription and returns the real number. Then the model can explain the result in a simple way. And this is how the LLM moves from being only a text generator to become a part of a real application workflow. It can search data, it can read the documents, check systems, query logs, create tickets, or trigger the automation. But tool calling also needs strong control. So in the production, we need permissions, input validation, output validation, and the logging. So for the sensitive actions, we may also need the human approval before execution. And this is important because once a model can use the tools, it can also affect the real system, not just generate text. Now let's talk about the grounding. So the grounding means connecting the model's answer to the reliable information. And that information can come from documents, databases, tool output, search results, or any trusted data source. So without the grounding, the model mainly answers based on what it has learned during the training or what was included in the prompt. Now that may be fine for the general topics, but it's not enough for the private company data, current information, or the regulatory environments. A simple way to understand the grounding is this. Before asking the model to answer, we give it real evidence. Then we ask it to answer based on that evidence. For example, if we are building an HR assistant, we should provide an approved HR policy documents. If we are building a cloud support assistant, we should provide logs, metrics, or troubleshooting documents. And this improves the accuracy and trust because the answer is based on the available evidence, not just the general knowledge. And it also helps with traceability because the system can show where the answer came from. So the grounding does not completely remove the hallucination, but it reduces the risk. It gives the model better information, limit guessing, and makes the answer more useful for the real world application. Now this brings us to the hallucination and the knowledge cutoff. So a hallucination happens when a model gives an answer that sounds confident, but the information is wrong, unsupported, or made up. And this is one of the biggest risks in the generative AI. The reason this can happen is that the model generates likely text. It is not a database and it does not automatically know whether every statement is correct at the time you ask the question. So if the prompt does not provide enough information, the model may try to fill the gap with something that sounds right, even if it's actually not. Let's take a simple example. If you ask the latest Azure pricing or a newly released feature, a model without browsing or updated information or documentation may give an outdated answer. The answer may sound professional and confident, but it may still be incorrect. And this is also related to the knowledge cutoff. A model is trained on the data available up to a certain time. It may not know what happened after that. And even if it knows the older information, that information may have changed. A simple example is asking someone about the restaurant prices based on the menu they saw 2 years ago. And they may remember the old price, but the current price could be different. And to answer correctly, they need to check the latest menu. Models have the same problem with the current information. In enterprise AI, hallucination is a serious topic. If AI is used for legal, medical, or financial decisions, a wrong answer can create a risk. So in cloud operations or the cybersecurity, a wrong answer can also cause the business impact. So how do we reduce the hallucination? We use grounding, RAG, and tool calling. We ask the model to answer from trusted sources. We use citations where possible. We validate the structured output. We test the system regularly. And for high risk use cases, we include human review. But let's be honest, hallucination cannot be fully removed just by writing a better prompt. It can be reduced, controlled, and monitored, but it cannot be completely ignored. Now let's connect the full video together. Prompt engineering helps us give the clear instructions to the model. System prompts define the model's role, rules, and the boundaries. Prompt templates help us reuse and standardize prompts across the application. Zero shot, one shot, and few shot prompting help us guide the model with or without examples. Now, reasoning patterns help the model handle more complex tasks. Structured output makes the response usable for other systems. Tool calling allows the model to work with the real tools and real data. And the grounding connects the answer to the trusted information. And the hallucination and the knowledge cutoff remind us that the models can be wrong, especially when the information is missing, outdated, or not properly grounded. And this is how we work with the models in the real application. We do not just ask the random question and hope for the best. We design the prompt, provide the right context, control the output, and connect the model to the trusted data or the logs or the tools. Then we evaluate and monitor the behavior over the time. So in this video, we covered the practical layer of working with the large language models. And this is the layer that turns an LLM from a simple chat interface into a useful enterprise application. So in the next video, we'll move into search, knowledge, and RAG. We will understand the vector search, hybrid search, and re-ranking. We'll also cover the chunking, metadata, and RAG evaluation because these topics are the heart of the most enterprise AI solution. And that's all for this video. So now in this video, we are going to move into another very important area, which is search, knowledge, and RAG. And this topic is very important because in real projects, a model alone is not enough. The model may not have your company data, it may not know the latest information, and sometimes it may give an answer that sounds correct but is not properly supported. And that is why search and knowledge becomes a very important part of the AI application design. So if we want to build useful enterprise AI solution, we need to understand how the models connect with the documents, data, and trusted sources. So in this video, we'll understand the main building blocks behind the search and RAG. We'll also talk about the AI search, knowledge retrieval, and how these concepts help reduce the wrong answers in the real world application. So the goal of the video is very simple. By the end, you should understand why search is important in generative AI, how knowledge is added to AI application, and why RAG is one of the most common patterns used in the enterprise AI solution. So let's start with the vector search. So in the previous videos, we already understood tokens, embeddings, and semantic meaning. So the vector search builds on the same idea. If the embedding converts text into numerical meaning, then the vector search uses those numerical representation to find the similar information. So in simple words, vector search finds information based on meaning, not only based on the exact words. So let's take an example. A user asks, how do I request time off? But inside the company's document, the heading may be annual leave process. So a normal keyword search may miss the best results because the user said time off, but the document says annual leave. So the vector search can still find the right information because of the meaning is similar, and it understands that the time off and the annual leave are related concepts. And this is why vector search is very useful in AI application, because users don't always ask questions using the exact same word that exists in the document. So now let's understand how this works at a high level first. So the documents are split into small sections, and we normally call these sections as the chunks. So each chunk is converted into embedding, which means each chunk gets a numerical representation of its meaning. Now these embeddings are then stored in the vector index or the vector databases. And when the user asks a question, the question is also converted into an embedding. And then the system compares the question embedding with the stored document embedding. So the closest matches are returned as a search result. And these top matches chunks can then be sent to the language model as a context. And this point is very important because the vector search is not generating the final answer. It's only finding the best candidate information. So the language model then uses that retrieved information to generate a clear response. Now, in real life, user ask questions naturally. They may use the different words, short sentences, or incomplete details. And vector search helps connect these questions with the right knowledge. Now, at a deeper level, vector search is trying to find the nearest neighbors, which simply means it's looking for the stored vectors that are close to the user's query vectors. So one common way to compare the similarity is called cosine similarity. We do not need to go deeper into the maths here, but the idea is simple. If the two vectors are close in the direction, the meaning is usually similar. But when you have thousands or millions of the chunks, comparing the question with every stored vector can become slow. So the production system uses smart indexing algorithm to make this faster. And one common algorithm you hear about is HNSW, which is hierarchical navigable small world. So for this video, you do not need to remember the full internal detail. Just remember that it creates a smart structure so the system can quickly find the closest result without checking everything. And this is how the services like Azure AI Search and vector databases can search large knowledge bases efficiently. So the simplest way to remember the vector search is: keyword search look for the matching words, but the vector search looked for matching meaning. And in the RAG system, this is powerful because the model does not need to know everything already. The system can first search the knowledge base, bring the most relevant information, and then ask the model to answer using the context. Now let's move from the vector search to the hybrid search and re-ranking. So in the last topic, we understood the vector search is very good at finding information based on the meaning. But in the real application, meaning is not always enough. Sometimes exact words matter. Sometimes IDs matter, sometimes product codes or the policy numbers or the service names matter. And this is where the hybrid search becomes useful. Hybrid search simply means combining more than one search method, usually the keyword search and the vector search. So the keyword search is strong when the exact item is important, and the vector search is strong when the meaning is important. Let's take a simple example. If a user asks about a policy with a specific policy ID, then the keyword search is very useful because the exact policy ID matters. We do not want the system to find something that is only similar in meaning. We want the exact policy. But if the user asks, can I work remotely from anywhere? The document may not use the same words, but it may say a remote work location approval or the working from another region. In that case, the vector search may find better results because it understands the meaning behind the question. So the keyword search and the vector search solve different problems, and the hybrid search brings them together. So in a production RAG system, this is important because the user can ask questions in different ways. Some questions need exact matching and some questions need semantic meaning. So the hybrid search gives us both. Now after the hybrid search results, we still have another challenge. The first search may return many possible matches. For example, it may return the top 50 results, but we do not want to send all the top 50 results to the large language model because that can increase the cost and add unnecessary noise. And this is where the re-ranking comes in. So re-ranking is a second step that looks at the retrieved results again and reorders them based on which one are the most useful for the user question. Now you can think of it like this. The first search step quickly collects the possible document, and the re-ranker acts like a reviewer that selects the best few results from that list. Now, this helps the model receive better context, and better context usually means a better answer. So let's take a cloud example. A user asks, why did my web application fails after the latest deployment? So the first search may retrieve the document notes, error logs, and the old troubleshooting articles. Some may be useful, some may be less relevant. So a re-ranker can push the most relevant deployment note or the error log to the top so that the large language model get the best evidence first. Same in Azure AI Search, you may hear about the semantic ranking, which is used to improve the order of the search result based on the meaning and the relevance. Now the idea is similar. We first retrieve the candidate results, then we improve the ranking so the best content is selected for the model. So simple way to remember this is keyword search find the exact match, vector search find the meaning based matches, and the re-ranking improves the final selection. And this is why in the real RAG system, hybrid search with the re-ranking is usually the stronger choice than using the vector search only. Now let's talk about the retrieval augmented generation or RAG. So in the previous topics, we understood the vector search, hybrid search, and the re-ranking. Now the RAG is where all these pieces start coming together. RAG is a pattern where the system first retrieves the relevant information from the trusted source, and that gives the information to the model before the model generates the answer. So a simple way to understand the RAG is open book answering. The model is not expected to remember everything by itself. Instead, we give it the right pages for the right sources at the time of answering. And this is very useful in the real AI application because the model may not know your private company data, latest policies, or the internal documents. For example, imagine you are building a company policy document. A user asks, how many days of the parental leave do I get? Now, the model should not guess this answer from the general knowledge. The system should first retrieve the correct policy section from the SharePoint, a document store, or a knowledge base, and then ask the model to answer based on that retrieved content. And this makes the answer more accurate and easier to trust. So a basic RAG flow works like this. The user asks a question, the system searches the relevant content, the best matching chunks are added to the prompt, and then the model generates an answer using the context. So if the application is designed properly, the answer can also include the citations, so the user can see where the information came from. And this is one of the main reasons RAG is so important in enterprise AI. It helps with the fresh knowledge, trusted sources, and access control. So fresh knowledge means the answer comes from your current documents, not only from the model's old training data. Trusted sources means the answer can be based on the approved documents, not random guessing. And access control means the system can retrieve only the information the user has allowed to see. But we should also understand the RAG is not just adding a vector database to an application. The RAG is a full architecture pattern. So behind the scenes, the document needs to be ingested, cleaned, chunked, embedded, and then indexed. So at a query time, the system may use the hybrid search, re-ranking, and the prompt templates before calling the model. So conceptually, RAG is simple, but in production, it needs proper design. The easiest way to remember RAG is that the first it retrieves the right knowledge, then asks the model to answer from that knowledge. This is how we reduce the guessing and build an AI application. Now let's talk about chunking and metadata. So in the previous topic, we understood that RAG retrieves the relevant information and gives it to the model before generating an answer. But one important question is, how do we prepare the documents so that they can be retrieved properly? And this is where the chunking comes in. So chunking means splitting a document into smaller pieces before storing it into the search index or the vector database. Now, these smaller pieces are normally called as the chunks. The reason we do this is simple. Most documents are too large to send to the model directly. And even if we could send the full document, it may include too much unnecessary information. So instead of giving the model the full document, we try to retrieve only the most relevant parts. But the chunking has to be done very carefully. If the chunk is too small, it may lose important context. For example, if the policy sentence says the approval is required, but the previous sentences explains what approval means, then retrieving only one small sentence may not be enough. On the other side, if the chunk is too large, it may include too much unrelated information, which wastes the token and confuse the model. So the good chunking is about the balance, and the right chunk size also depends on the document type, structure, and the use case. So a technical architecture document may need different chunking compared to the HR policy or a product manual. Some systems use the fixed size chunking, where each chunk is around a certain number of the tokens. Some systems splits by the natural boundaries like the headings, paragraph, and sections. And more advanced systems can use the semantic chunking, where the split is based on the meaning. Now, the main goal is same. Each chunk should be big enough to carry the useful context, but small enough to stay focused. Now, metadata is the second important part. Metadata means extra information attached to the each chunk. For example, a chunk can have the metadata like the document title, section name, and the version. So in an enterprise system, metadata can also include the department or environment or access level. And this is very useful because the search is not always about finding similar text. Sometimes we need to filter the result before searching. For example, in an HR policy assistant, metadata can help return only the current HR policies and ignore the older versions. So in a cloud assistant, metadata can help filter the content by subscription, environment, or the workload. So if the user is asking about a production issue, we may want to retrieve the production runbooks, not the development notes. So the metadata also helps with the security because the system can filter the content based on what the user is allowed to access. And this is very important in enterprise AI because not every user should see every document. So a key message is this: RAG quality is not only about the language model. Even the best model can give the poor answers if the retrieved chunks are weak or the metadata is missing. So the good chunking helps with the system retrieve the right amount of information or the right amount of text, and good metadata helps with the system retrieve the right context for the right user and situation. Now let's talk about the vector databases. So in the previous topic, we understood that the documents are split into chunks and those chunks are converted into embedding, and then the system needs to search those embedding where the user asks a question. So a vector database is the place where these embeddings are stored and searched efficiently. You can think of it like a semantic library index. So in a normal library, you may search by book title or author. In a vector database, the system searches by meaning. It stores the embedding, the original text or the relevance to the original text, and the useful metadata like the document name, section, version, or access level. When a user asks a question, the question is also converted into an embedding, and the vector database returns the closest matching chunks. For example, an enterprise knowledge assistant may store the chunks from policies, architectural documents, and runbooks. So when a user asks a question, the vector database helps find the most relevant parts of those sources, and then the language model uses those parts to generate an answer. And this is an important point to remember. A vector database does not replace the large language model. It does not normally write the final answer. Its job is to help the model find the right source material. The model then uses the retrieved content to create a human-friendly response. And there are different types of the vector stores available. For example, Azure AI Search is commonly used in the Microsoft-based solution because it supports the vector search, keyword search, and the semantic ranking. So Pinecone is a fully managed vector database. Similarly, Quadrant, VV8, and Milvus are popular specialized vector databases. So Postgres can also support the vector search using the PG vector, which is useful when you already have the data in the Postgres and want the vector search close to your existing database. So the right choice is not only about which database has the best algorithm. It also depends on scale, cost, and operation. So it also depends on filtering, security, and how well it fits into your existing platform. If you are building on Azure, Azure AI Search is often a natural choice. If your application already uses Postgres, the PG vector may be a good option. If you want a specialized vector databases, then tools like Pinecone, Quadrant, or Milvus may be considered. So the simple way to remember this is a vector database is not the brain for the AI system. It is the knowledge index that helps the brain find the right information at the right time. Now let's talk about the RAG pipeline. So until now, we have discussed vector search, hybrid search, re-ranking, chunking, metadata, and vector databases. But in the real application, these are not separate ideas. They work together as one full pipeline. So a RAG pipeline is the complete process used to prepare the data, retrieve the right knowledge, and generate an answer from that knowledge. So this is why we should not think of RAG as just adding a vector database to an application. RAG is a full architecture pattern. Let's take an example of the company policy chatbot. First, we need to bring source documents into the system. These documents may be the PDF, Word file, or the pages from the knowledge bases. After that, the document needs to be parsed and cleaned so that the system can remove the unnecessary formatting and extract full text. Then the content is split into the chunks. Metadata is added and the embeddings are created for those chunks. And after that, the chunks and embedding are stored in the search index or the vector database. And this is the preparation side of the pipeline. And it normally happens before the user even asks a question. Now, when the user asks a question, the query side of the pipeline starts. The user's question may be converted into an embedding, and then the system searches for the most relevant chunks for that embedding. Now, in a production system, it may use the hybrid search, so it can combine the keyword matching as well as the meaning based search. And then the re-ranking can improve the order of the result so that the best chunks are selected. After that, these selected chunks are added into the prompt along with the clear instructions. For example, the prompt may say, answer only from the provided content. Cite the source and say clearly if the answer is not available. Then the model generates the final response based on the retrieved content. So if the system is designed well, the answer can also include the citations, so the users can verify where the information came from. So around this main flow, we also need the production controls. We may need caching to improve the performance, content safety to reduce the risk, and observability to monitor what's happening. We also need evaluation because we need to know whether the system is retrieving the right content and whether the model is giving a grounded answer. So in Microsoft based solution, most parts of this pipeline can be built using the Azure AI Search and Microsoft Foundry. So Azure AI Search can help with indexing, vector search, and semantic ranking. Foundry can help with orchestration, model integration, and evaluation. But the main concept is platform independent. Whether we use the Azure, open source tools, or another cloud platform, the RAG pipeline's idea stays same. We prepare the knowledge, retrieves the best content, and then ask the model to answer from that context. Now let's talk about the RAG evaluation. So in the previous topic, we understood the full RAG pipeline, where the documents are prepared, searched, and then passed to the model as a context. But after building the pipeline, one very important question comes. How do we know if this is actually working? So this is where the RAG evaluation becomes important. So in normal AI demos, we often look at the final answer and think, and yes, this sounds good. But in production, that's not enough. A RAG system can give a very nice looking answer. But if it retrieved the wrong document or used the unsupported information, the answer can still be wrong. So we need to evaluate both parts, retrieval and generation. So retrieval evaluation checks whether the system found the right chunks from the knowledge base, and generation evaluation checks whether the model used those chunks correctly to create the final answer. Let's take a simple example. A user asks about the parental leave policy. The RAG system must first retrieve the correct parental leave section from the policy document. If it retrieves a general policy document or an old version of the document, then even a strong model can produce the wrong answer. So if the answer is wrong, we need to know where the failure happened. Did the retriever miss the right chunk, or did the model ignore the context chunk and generate something unsupported? Now this distinction is very important because the fix is different. If the retrieval is the problem, we may find a better chunking, metadata, or search ranking. If the generation is the problem, we may need a better prompt, a strong model, or a stricter grounding instructions. So the common RAG evaluation checks include whether the answer is grounded in the provided context, whether it answers the user question, and whether the retrieved chunks were actually relevant. We also need to check citations because if the system shows the wrong source, the user may trust an answer that is not properly supported. So in the enterprise system, we should not rely only on the random testing. We should use the real user questions, expected answers, and repeatable test results or the test sets. So this helps us measure whether the changes are improving the system or making it worse. For example, if we change the chunk size or add the re-ranking, we should be able to compare the results before and after. Tools like Ragas, Microsoft Foundry evaluations, and the Langsmith can help measure the different parts of the RAG system. But the main idea is simple. We cannot improve what we do not measure. So the RAG evaluation help us check whether the system is retrieving the right knowledge, generating a grounded answer, and giving user a response that they can actually trust. So now let's talk about the fine tuning versus the RAG. And this is very common question in AI projects because many people think both are used for the same purpose, but they solve the different problems actually. RAG is useful when the model needs access to the private, fresh, or changing information. Fine tuning is useful when we want to change the behavior of the model. Let's take a simple example. If your company updates the HR policy documents every month, you should not fine tune the model every time the policy document changes. That would be expensive and hard to manage. Now, in this case, RAG is a better option because the system can retrieve the latest policy at answer time and give it to the model at context. But if your support team wants every response to follow a very specific tone, format, or a classification style, then the fine tuning may help because you are not giving it the new knowledge. You are trying to teach the model a consistent behavior. So the simple rule is this. RAG helps with what the model knows at the runtime, and the fine tuning helps with how the model should behave. So in the real enterprise applications or the systems, we often use both of them together. So the RAG can provide the latest information from the documents, tickets, or the system, while the fine tuning can improve the response style or the task specific behavior. For example, a customer support assistant can use the RAG to find the latest production information, but the fine tuning may help it follow the company's preferred response structure. So we should not think of the fine tuning and RAG as the competitors. They are the different tools for the different needs. If the information changes often, use RAG. If the behavior needs to be consistent, consider fine tuning. And if you need both current knowledge and the consistent behavior, then both pattern can work together. Now let's talk about the graph RAG. Until now, we have mostly discussed RAG as a pattern where the system retrieves the related chunks or the relevant chunks and give them to the model as context. Now, this works well for many use cases, especially when the question can be answered in a few relevant sections. But sometimes the question is not only about the finding the similar text. Sometimes the question needs the relationship across many documents, system, and the people. And this is where the graph RAG becomes useful. So GraphRag combines the retrieval with graph-based knowledge representation. So in simple words, it does not only look for the similar chunks, it also tries to understand the entities and the relationship. So an entity can be an application, a database, or a team, and a relationship that can show that an application depends on a database, a team owns a system, or an incident is connected to the workload. So instead of only asking which text is similar to this question, GraphRag also help answer how are these things connected. Let's take an enterprise example. Suppose you ask which application depend on the database and which teams owns them. So a simple vector search may find a few documents where the database name appears, but the full answer may be spread across the multiple architectural documents, CMDB records, and ownership notes. Now, one document may mention the database, another document may mention the application, and another source may mention about the support team. So the graph RAG can help connect these pieces and give a more complete flow. And this is why the graph RAG is useful for the complex knowledge landscapes. It can help when the answer needs a multi-step connection, not just one matching paragraph. For example, it can be useful in an enterprise architecture, security investigation, and the research scenarios. So if you're just building a simple FAQ bot, you may not need the graph RAG. Normal RAG with a good chunk and search can be enough. But if your use case depends heavily on the relationship, then graph RAG can become powerful. So a simple way to remember this is normal RAG is good when you need the right document or the chunks, but the graph RAG is useful when you need to understand how the different findings are connected. It adds a relationship layer on top of the knowledge retrieval so that the model can work with a more connected view of the information. Now let's talk about the agentic RAG. So normal RAG usually follows a fixed flow where the user asks a question, the system retrieves the relevant chunks, and the model generates an answer from that context. Now this works well when the question is simple and one retrieval step is enough. But some questions need more investigation, and this is where the agentic RAG becomes useful. So the agentic RAG is more active form of RAG where an agent controls the relevant process instead of doing one search. So the agent can plan what information is needed, search multiple sources, refine the query, call different tools, compare the result, and decide whether this information is enough to answer or not. Let's take a cloud operations example. A user asks, why did the application fail after the deployment? A normal RAG system may search the document base and return a few related chunks. But an agentic RAG system can do more. It may first search the document notes, then retrieve the architectural document, then check the latest logs, and after that create a structured answer with the most likely cause and the next steps. So a simple way to understand this is to compare normal RAG with asking a librarian for the best pages from a book. Agentic RAG is more like asking a research assistant to investigate across the multiple sources and come back with a complete answer. This can improve the results for the complex question, especially when the answer is spread across the different systems or when the system needs multiple steps. But we should also be practical. Agentic RAG can add more latency, more cost, and more operational complexity because the agent may perform multiple searches and the tool calls before answering. So we do not need agentic RAG for every use case. For simple questions, normal RAG may be enough. For complex troubleshooting, investigation, or the multi-source questions, agentic RAG can be very powerful. The simple way to remember this is normal RAG retrieves the context, but the agentic RAG investigates the context. It gives the system more control over what to search, when to search again, and how to verify whether the retrieved evidence is enough or not. Now let's connect the full video together. In this video, we understood how search, knowledge, and RAG help large language model work with the right information instead of only depending on what the model already knows. We started with vector search, where the system finds information based on the meaning. Then we understood the hybrid search and the re-ranking, where the exact match and the system matching work together to improve the retrieval quality. After that, we looked at the full RAG pattern, where the system retrieves the trusted information and give it to the model before generating an answer. We also understood why chunking and metadata are so important, because the poor chunks or the missing metadata can make even a stronger model give a weak answer. Then we discussed the vector databases, RAG pipeline, and the RAG evaluation, which are important when we move from a simple demo to a real enterprise application. We also compared the RAG with the fine tuning and understood the RAG is better for changing knowledge, while the fine tuning is better for consistent behavior. Finally, we looked at the graph RAG and the agentic RAG, which are useful when the question needs relationship, investigation, and multi-retrieval steps. So the main message is simple. In the real AI application, the model is only one part of the solution. The quality of answer also depends on how well we search, retrieve, and provide the right information to the model. So in the next video, we'll move into another important area of generative AI, where we'll understand the agents, tools, and how AI system can perform more advanced tasks beyond simple answering questions. So until now, most of our discussion was focused on the text because that is how many people first experience AI. We type a question, the model processes the prompt, and then it gives us a text response. But in the real world, information does not always come as the text because sometimes the important context is inside an image or a screenshot, a scanned document, or even a voice conversation. And because of this, modern AI is now moving towards or beyond simple text interaction into something more natural or much closer to how humans actually communicate. So today, users don't always want to type the long prompts to explain a problem because In many situations, it is much easier to just upload a screenshot or share a dashboard or speak naturally with a voice assistant instead of describing everything manually. And this shift is changing how AI applications are designed because every type of interaction brings the different requirements. A normal text chatbot behaves very different from a voice assistant because in the voice interactions need fast responses and natural timing, while image understanding and the image generation solve completely different problems, since one focuses on analyzing the visual information and other focuses on creating it. And once we move into the video generation, the complexity increases even further because now the system must manage the movement, the timing, the consistency across the many frames instead of just one frame or one image. So in this video, we are going to understand how AI systems are expanding beyond text and becoming more multimodal. We, so in this video, we are going to understand how AI systems are expanding beyond text and becoming more multimodal. We will discuss the multimodal AI, vision language models, image and video generation, and finally the voice AI with the real-time AI. Now, the goal is not just to understand the technology itself, but also to understand where these capabilities are becoming important in enterprise application and what we need to think about when designing these type of systems. Now, let's start with the multimodal AI. The word multimodal simply means the AI system can work with more than one type of input or output. So instead of processing only text, the model may also work with the images, audio, or the video. And this is important because the humans naturally communicate using the multiple forms of information together. We read documents, look at the visuals, listen to the conversation, and understand the context from many different formats at the same time. So modern AI systems are now moving in a very similar direction. So instead of forcing users to convert everything into text before interacting with the AI, multimodal systems allow people to work more naturally with the information they already have. So rather than typing a long explanation about an Azure issue, someone may simply upload a screenshot and ask the model what went wrong, while other user may share a business chart and ask for a quick summary of the trend without manually explaining the entire dashboard. In the same way, someone working with the scanned forms or the receipts may directly ask the AI to extract the information from the image itself. So the interaction starts feeling less like using a traditional software tool and more like working with an assistant that can understand different forms of information together. Now, many modern models are already moving in this direction. For example, GPT 5.5 supports both text and images. Gemini models are designed for multimodal use cases, and 5 models support text, audio, and the vision together. Now, what this really means is that the AI systems are becoming more flexible in how the users communicate with them, because instead of treating AI as only a text interface, we can now think about it as a system that understands the information in a much broader and more natural way. So this becomes especially useful in enterprise environment because organizations do not store knowledge only in the written document. Important information may exist inside the architectural diagrams, scanned contracts, operational dashboards, or even the recorded calls, which means users often need help understanding the information that is not purely text based. So a multimodal AI system helps bridge this gap by allowing the users to interact with the system using the same format they already work in the real life. Also, at the same time, multimodal AI also introduces new challenges because every type of interaction has a different quality, latency, and cost requirement. So, evaluating a text response is very different from evaluating a image-based answer. And building a voice assistant is also very different from building a document assistant. So, while multimodal AI makes the user experience more natural, it also requires more careful architecture and system design behind the scenes. Now let's move into the vision language models, often called as the VLMs. So in the previous topic, we discussed multimodal AI in general, where a system can work with the different types of information together. So a vision language model is more focused because it specifically combines the visual understanding with the language reasoning, which means the model can look at the image and then explain or reason about what it sees using the natural language. And this becomes extremely useful because many real world problems are visual in nature. So in cloud and DevOps environment, engineers constantly work with the architectural diagrams, dashboard, monitoring, graphs, and error screenshots. While in the business operations, people regularly work with the invoices, forms, and the scanned reports. So instead of manually analyzing all this information, users can now ask AI to help interpret what is visible inside the image. For example, someone may upload an Azure architectural diagram and ask the model to identify the possible security risk. And the AI may notice that an application appears publicly exposed or that design does not allow or show the private endpoint or logging requirements or components. So in the same way, a user analyzing a dashboard may ask the AI to explain the trends or anomalies directly from the chart without manually describing every metric. So the model is not only reading the text anymore because it is combining the visual context and the user's instruction, then generating a meaningful response. Now, the current examples of the vision capable models include the GPT 5.5, Gemini, and the Claude. While smaller models like Microsoft 5 for multimodal also support the text, vision, and audio together, which becomes very useful when lower cost or lower latency is important. But even though these systems are powerful, but they are still not perfect because a VLM may misunderstand a complex diagram, miss small details, or incorrectly interpret text inside an image. And because of this, important decisions should be validated by humans. So the real value of the VLM is not that they completely replace the human review, but they significantly improve how quickly the users can analyze the visual information and extract the useful insight from it. Now let's talk about the image generation. So earlier we discussed models that understand the images, but the image generation is different because now the AI creates a new visual content instead of only analyzing the existing visuals. So in simple words, the model takes a prompt and generates an image based on that instruction. So this area has become very popular because it allows the user to quickly create the visual concepts, marketing material, or creative content without starting from scratch. So instead of spending the hours creating an early design manually, users can generate the visual ideas much faster and then refine them further based on what they need. So the image generation is no longer only about the creativity because it is increasingly becoming part of the normal business workflow as well. And today, different image generation models are available for different type of use cases. Like GPT Image 2 supports the image creation and editing workflows. Gemini can support the multi-model generation scenarios, and Adobe Firefly is often preferred in the environment where the commercial safety and the licensing are important. And at the same time, good image generation still depends heavily on the prompt quality because the output improves when the instructions become more clear and detailed. Things like the visual style, aspect ratio, and the brand consistency becomes very important, especially when the generated content is being used for business purpose. Organization also need to think carefully about responsible usage because AI generated visuals can sometimes look extremely realistic, which creates the concern about copywriting, misinformation, and brand protection. So even though the image generation is powerful, good results still depend on the careful prompting, proper review, and responsible use. Now let's move into the video generation, which takes the idea even further because instead of generating a single image, the AI now creates the moving visual content. And this becomes much more complex since the system must maintain the consistency across the multiple frames while also handling the movement, timing, and visual transition in a natural way. And this technology is growing very quickly because it can reduce the effort required for early stage content creation and storytelling. So instead of producing a complete professional video from day one, teams can first generate rough visual concepts, animated storyboard, or short simulation clips to quickly explore ideas before investing more time and money into the full production work. So the current examples include the Google Veo, Runaway Gen 4 and Adobe Firefly Video. So OpenAI's Sora also demonstrated how advanced this space has become. Although the organization should always check availability and the licensing before planning the production use around these specific models. And compared to the image generation, video generation requires much more processing because the AI must keep the object, scenes, and motion consistent over the time. And this is why the current system can still struggle with realistic movement, object consistency, and visual artifacts in the longer scenes. So while the technology is impressive, production use still requires editing, quality review, and proper human oversight. Just like image creation, organizations also need to think carefully about responsible usage because a realistic generated video can easily be misunderstood as a real footage. So finally, let's talk about voice AI and real-time AI because this is where the AI interactions start feeling much more human. Until now, we mostly discussed about typing, images and the visuals, but voice changes the experience completely because users can simply speak naturally with the system instead of typing the prompt manually. So the voice AI allows the user to communicate using speech while the real-time AI focuses on making that interaction fast enough to feel like a live conversation. And this becomes especially important for customer support, training, or conversational enterprise systems because the user expect the interaction to feel smooth and natural instead of delayed and robotic kind of. For example, instead of typing the question into a chatbot, a customer may directly speak with an AI powered insurance assistant that will listen to the request, check the information using the RAG or connected tools, and then respond back conversationally using voice. And from the user's perspective, this feels simple and natural. But technically, it is much harder than a normal chatbot because the latency becomes extremely important. So, in a text conversation, waiting a few seconds may still feel acceptable, but in a live voice interaction, even a small delay can make the experience feel awkward. And the system also need to understand the pauses, interruptions, and the background noises while responding naturally in the real time. So the traditional voice system often followed a pipeline approach where the speech was first converted into text, then processed by the language model, and finally converted back into the speech again. This still works today, but the newer real time models are now handling audio interactions more directly, which makes conversation feel smoother and much more natural. So the examples in this space include the OpenAI GPT Real Time, Google Gemini Live, and Azure AI Foundry Voice Live. So these systems are designed for the low latency conversational experience where AI can listen, reason, and respond almost instantly. So in an enterprise environment, this becomes very powerful when combined with the tools and the RAG because the assistant can now not only speak naturally but can also retrieve the information or specific business information and help the user complete the task during the conversation itself. But the production voice AI systems still require careful design because we need proper testing, safety control, and escalation paths to the human, especially when the customers or sensitive information are involved. So the important idea here is that AI makes interaction more natural, while real-time AI makes it feel truly conversational. Now, let's connect everything together. In this video, we moved beyond traditional text-based AI and explored how modern AI systems are becoming much more multimodal. We discussed how AI can work with images, audio, and video instead of just the text. We understood how the vision language models help analyze the visual information, how the image and video generation models create the new content, and how the voice AI with the real time AI enables natural conversation. So the main message is simple. AI is no longer limited to typing questions and repeating text answers because users now expect to upload the screenshots, analyze visuals, and speak naturally with the assistant in the same way they interact with the people in the real life. And this makes AI systems more useful and more human like. But it also introduces the new challenge around the latency, safety, cost, and evaluation. Now, different experiences require different architectural decisions, which means a voice assistant, a document assistant, and an image generation application all need different design approaches. So, as the AI continues moving beyond text, the real focus should not only be on the model themselves, but also on designing safe, useful, and reliable user experience around them. So that's all for this video. In the next video, we'll continue building on this foundation and move into another very important area of generative AI, where we'll understand how AI agent works, how they use the tools, and how they can perform more advanced tasks in the real applications. So now in this video, we are going to move into one of the most important areas of the modern AI, which is agents and agentic systems. Now, this topic is becoming very important because AI is no longer only about asking questions and getting the answers. In real applications, organizations want AI system that can follow the goals, use the tools, and complete the task across the multiple steps instead only gathering the text or providing the text information. For example, instead of asking an AI assistant to simply explain an application alert, we may ask the system to actually investigate the issue by checking the logs, reviewing the runbooks, and then preparing an incident summary before suggesting the next action. And this is where the agents become more powerful because the AI is no longer only responding to the prompts, it is now participating in the workflow and helping complete the real operational task. So in this video, we'll first understand what an AI agent is, how is it different from the normal chatbot, and then we'll move into memory, planning, and tool use because they are the core capabilities that make the agent useful. And after that, we'll discuss the multi-agent system where the multiple specialized agents can work together with the different responsibilities. We'll also understand the MCP and A2A because these standards are becoming important for connecting the agents with the tools and with the other agents. And finally, we will look at the LLM application frameworks and understand why they help the developers build these systems faster and in a more structured way. So the goal of the video is simple. By the end, you should understand what the agents are, why they matter in the real projects, and how the agentic system help AI move beyond the simple text generation into systems that can actually assist with the real work. Now let's start with the AI agents. So until now, most of our discussions were focused on the models that answer questions, generate text, or process the different types of information. But an AI agent goes one step further because it is not only generating a response. An agent is a system built around the model that can follow a goal, decide what to do next, and take the actions using those tools. So a normal chatbot may answer a question like, what does this Azure alert mean? But the agent can continue working through the problem by checking the logs, reviewing the monitoring information, reading the documentation, and then using all the information together before preparing a meaningful response. Now, this is the biggest difference between a chatbot and an agent. A chatbot mainly responds while an agent works through a step-by-step task. So let's take an Azure SRE example, which is Site Reliability Engineer example. Suppose an application suddenly becomes slow. So instead of only explaining what the alert means, an agent can first inspect the monitoring alerts, then review the application logs, then check the recent deployment changes, and finally identify the most likely cause before suggesting remediation steps or preparing an incident summary. So the important idea here is not only the response itself, but the loop behind it. The agent removes a goal, takes an action, observes the result, and then decides what to do next. And some of the agents may be simple and only use one or two tools, while others may continue working across many steps depending on the complexity of the task. But one thing is very important to understand here. An agent is not just like an LLM by itself. It's an application pattern built around the model, which means it can also needs the tools, memory, planning, permissions, and the guardrails. Because once an agent starts interacting with the real system, it can affect the actual business operation. And this is why we should not use the agents everywhere just because the idea looks powerful. If a simple answer is enough, then a normal LLM call may already solve the problem. But when the task require the investigation, tool usage, or multiple steps, the agent become extremely useful. So the simplest way to remember this is a chatbot answers, but an agent acts. Now let's move into memory, planning, and tool use, because these are the core capabilities that allow the agents to work properly. So in the previous topic, we understood that the agents can follow the goals and work through tasks. But for that workflow to function properly, the system needs memory to retain the context, planning to organize the action, and tools to interact with the external system. Now, memory allows the agents to remember useful information, either during the current interaction or across the longer period of time. So the short-term memory may include the current conversation, where the system remembers what the user just asked, while the long-term memory may include the user preferences, previous decisions, or important project context. So instead of repeating the same instructions every time, the agent can continue working through the information it already learned earlier. Now, planning is equally important because the agent should not randomly perform actions without the structure. If the goal is to investigate an outage, the agent may first review the alert, then analyze the logs, and then inspect the deployment changes in a logical sequence instead of just jumping between the unrelated tasks. Now, this makes the workflow more organized and useful because the system is thinking through the task step by step. Then we have tool use, which is one of the most powerful capabilities of the modern agents, because tools allow the agent to interact with the external system instead of only generating the text. The agent may search the document, call the API, query the monitoring system, or create the tickets depending on what the workflow requires. For example, an Azure operations agent may retrieve monitoring data, analyze the logs, and then create the incident summary automatically using the connected system together. And this is where the AI starts becoming more practical, because instead of only explaining something, the system can actively help complete the parts of the workflow itself. But once agent gain memory or the tool usage, security becomes extremely important, because these system can now interact with the sensitive data and the real business system. So the organization must carefully decide what information the agent can remember, what tools it can access, and which actions require the human approval before the execution. Now, the simple way to think about this is that memory helps the agent retain useful context, planning helps to organize the workflow, and the tool allow the agent to take action outside of the model itself. So let's talk about the multi-agent system. In the previous topic, we understood how a single agent can use the memory, planning, and tool to complete a task. But sometimes one agent is not enough, especially when the workflow contains very different responsibilities that need clear separation. And this is where the multi-agent system becomes useful, because instead of just relying only on the one large agent to do everything, the work can now be divided across the multiple specialized agents. For example, if we are building a cloud cost optimization solution, one agent may collect the usage data, another may analyze the cost saving opportunities, and another may prepare the final report for the customer. Now, each agent focuses on a specific responsibility, and together they complete a larger workflow. So in the same way, a healthcare workflow may involve one agent reading the incoming document, while the another verifies the patient details, and the another one checks the appointment availability. So the system becomes more structured because the different responsibilities are clearly separated. But this is also where we need to be careful, because more agents do not automatically create a better system. As the number of the agent increases, the workflow now becomes slower, more expensive, and much harder to debug. So if the final output becomes incorrect, it may be difficult to identify which agent created the problem or whether the issue happened during the communication between the agents. And because of this, it's usually better to start with a simple design and move towards a multi-agent system only when there is a genuine need for the role separation or the permission separation or specialized workflow. For example, in a banking environment, a customer service agent may need to work together with a fraud agent or an approval agent, because each one have their different permissions and the control. Now, in that kind of scenario, separating the responsibilities become useful and safer. So the important idea here is that the multi-agent system should solve a real architectural problem, not simply increase the complexity for no reason. So start simple and only introduce the multiple agent when the specialized collaboration is genuinely needed. Now let's move into MCP, which stands for Model Context Protocol. So MCP was introduced by Anthropic to solve a very common integration problem in AI applications. So when we build agents, those agents often need to interact with the external systems like the databases, cloud platforms, repositories, or internal documentation. So without a standard approach, every AI application would use a separate custom integration for every tool, which quickly becomes difficult to manage. Now, MCP provides a more standard approach for the agents to connect with the tools and contexts. Now, a simple way to think about MCP is that it can act as a connector standard for AI systems. So instead of building completely custom integration every time, the agents can communicate with the MCP servers that expose tools, resources, and prompt in a very structured way. For example, an AI assistant may connect with the GitHub MCP server to work with the repositories, an Azure MCP server to interact with the Azure services, or a file MCP server to read the local files. So instead of AI only generating the text response, it can now interact with the real system in a more organized and reusable way. So MCP server themselves can expose the different types of capabilities. So tools represent actions the agents can perform. Resources represent the information the agent can access, and the prompts can provide the reusable instruction or the template that help guide the model during the execution. And there are also different deployment models for MCP. Some MCP server may run locally on a developer machine, while other may run remotely inside an enterprise environment or managed by the vendor itself. And this flexibility becomes useful because the organizations can decide how and where these interactions should operate depending on the security and the operational requirement. But once again, security becomes extremely important because MCP interactions may expose the sensitive system and powerful actions. So if an agent can read files, access databases, or trigger the deployments, then organizations need authentication, authorization, logging, and least privilege control. So the simple way to remember MCP is this. MCP helps agent connect with the tools and the context through a standard interface, but because these tools can interact with the real system, security design becomes just as important as the interaction itself. Now let's move into A2A, which stands for Agent to Agent Communication. So A2A was introduced by Google to help the different agents communicate and collaborate with each other in a more standard way. Now, this is different from MCP because MCP mainly focuses on connecting the agents with the tools and the data sources, while A2A focuses on connecting one agent with the another agent. So a simple way to think about this is the MCP helps the agent use the tools while A2A helps the agent work together. For example, a travel planning assistant may need to coordinate with the separate booking assistant, payment, and the scheduling agent, where each one handles a specialized part of their workflow. Also, in enterprise environment, a procurement agent may communicate with a finance approval agent and a vendor management agent so that overall process can move across the different system and responsibilities more smoother. Now, one important concept inside A2A is the agent card, which is similar to a profile that describes what the agent can do, how it can be contacted, and what type of the task it can support. Now, this becomes very important as the organization begin using many specialized agents from the different platform and the vendors, because those agents need a common way to identify and communicate with each other. But just like MCP, A2A also requires the strong controls because one agent start communicating with other agents, the organizations need the identity management, authentication, logging, and the clear permission boundary to ensure one agent cannot trigger unsafe behavior in the another system. Now, the simplest way to remember this is that the MCP connect the agent with the tool while A2A connect the agent with the other system. And both are important for the modern agentic systems, but they solve the different problems. Now let's talk about the LLM application frameworks, because when the developers start building these systems in the real projects, they usually do not want to create everything from scratch every single time. And this is where the frameworks become very useful because they provide the reusable building blocks for the prompts, tools, workflows, orchestration, and even the memory management. For example, if someone is building a RAG assistant, a framework can help connect the model with the vector stores, manage the prompt, and coordinate the retrieval workflow more easily. Now, if someone is building an agent system, the framework can help manage the execution state, multi-step workflows, tracing, and orchestration logic. Now, different frameworks focuses on the different use cases. So, LangGraph is often used for the stateful workflow, where the developers want more control over the execution path. Crew AI, if you have heard about it, is more popular for the role-based multi-agent system, where the different agents collaborate like a team. And then we have the Microsoft Agent Framework, which is new and is especially useful for the Azure and Microsoft aligned environments where the organizations want the enterprise integrations and orchestration support. And there are many other options such as OpenAI Agents SDK, Llama Index Workflow, and the Google Agent Development Kit, depending on the platform and the type of the application being built. But one thing is very important to understand here. The frameworks are not magic. They can speed up the deployment process, but they do not automatically create the good system. So if the underlying prompt design, retrieval quality, or the security control are weak, then adding a framework will not solve anything. And the real quality still comes from understanding the fundamental properly and designing the overall workflow carefully. So when selecting a framework, the goal should not only be choosing the most powerful framework or popular one. The more important question is that the which framework fits the architecture, operational requirement, and the skill set of the organization. Now let's connect this together. So in this video, we understood how AI is moving beyond the simple question answers into agentic system that can plan, use tools, and complete the task across the multiple steps. We started with the AI agents and understood that an agent is not just an LLM because it's an application pattern built around the model with the goals, workflows, and actions. Then we explored the memory, planning, and the tool use because these capabilities allow the agents to retain the context, organize the task, and interact with the external system. And after that, we discussed the multiple agent system and understood what specialized agents are and how they can collaborate together when the workflow requires the clear role separation or the different permissions. We also explored the MCP and the A2A, where MCP helps the agents connect with the tools and the context, while A2A helps the agent communicate with the other agents. And finally, we looked at the LLM application frameworks and understood that the frameworks can accelerate the development, but they still require the strong architecture evaluation and the security design itself. So the main message is simple. The agents become powerful because they allow the AI system to move beyond only generating answers and start helping with the real operational workflows. But as these systems gain access to the tools, memory, and the external system, strong governance, security, and guardrails become even more important. So in the next video, we'll continue with the journey and move to the another important area of generative AI, where we'll understand how to properly design these systems for the production governance and the real enterprise use case. Now in this video, we are moving into a new important stage, which is production and enterprise readiness. Now, this is the point where we stop thinking about the demos and start thinking about the system that users, teams, and organization can actually depend on safely in a real environment. Now, in a demo, it may be enough if the model gives one impressive answer. But production system needs much more than that because the application must remain reliable when the users, prompts, and data continuously change over the time. We need the right models for the right task, the right deployment strategy, and the right architecture around the application. We also need monitoring, evaluation, and security because the generative AI systems behave different for the traditional softwares. Now, small changes in the prompts, retrieval results, or the model versions can change how the application behaves, which means the production AI system need much stronger operational practices than the simple prototype. Now, this topic is especially important for the architects and the developers because building a real AI application is not only about calling a model API. We need to think about routing the request to the different models, deciding where the model should run, and managing how the application behaves in the production. We also need to think about the governance, benchmarking, responsible AI, and the cost optimization. So the final solution is accurate, safe, and affordable at scale. So the goal of this video is simple. By the end, you should understand what it really takes to move a generative AI solution from a working prototype into an enterprise-ready production system. Now let's start with the model routing. So in production AI application, we should not assume that every request need to go to the same model because different tasks have different requirements. Some requests are simple, some need deep reasoning, and some may require the specialized capabilities like image understanding or the tool usage. Now, model routing is the process of sending each request to the most specific model based on the task, latency requirement, and the cost considerations. For example, a simple FAQ request or the classification task may work perfectly with the smaller or the cheaper model, while a complex architecture review or the advanced troubleshooting request may need a stronger reasoning model. Similarly, if the request may contain an image, the system may automatically route it to the vision capable model instead to the normal text model. So instead of using the most expensive model for everything, the application becomes smarter about how it handles the different workloads. And there is also an important difference between the model selection and the model routing. So the model selection happens during the design stage when we decide which model are suitable for the application overall, while the model routing happens at the runtime because the system looks at the actual incoming request and decide which model should process it. And some routing approaches can be very simple and rule based. For example, the application may send lightweight tasks to a smaller model or reserve the stronger model only for the complex reasoning. Now, if I'll talk about the more advanced routing system that can dynamically inspect the request and decide automatically which model is the best fit. So in Microsoft Foundry, model router follows the same pattern because it behaves like a deployed model endpoint, while internally deciding which underlying model should actually handle the request. Now teams can optimize for quality, cost, or a balanced request, both depending on the business requirement. And this becomes especially useful in the production system where there is a high volume application often need the different behavior for the different workload. So a customer support assistant may route the basic questions to the smaller model while sending the complex troubleshooting or the sensitive architectural questions to the stronger reasoning model. And the organization may also apply the routing rules based on the region, compliance requirement, or approved model policies. So the biggest benefit of model routing is flexibility because it helps reduce cost, improve the performance, and optimize the quality across the different scenarios. But routing also needs proper evaluation because we must ensure the router is consistently choosing the correct model and meeting the security and compliance requirement. So the simple way to remember this is that the model selection happens during the design while the model routing happens dynamically at the runtime of the each request. Now let's move into the model deployment and hosting. So once we choose the right model, the next question comes how we actually make the model available for our application. And this is what the deployment and hosting are about. Because the model needs to run somewhere so that the application can call it or receive the responses. The easiest option here is usually a managed API provided by a cloud platform or the model provider. So in this approach, the provider manages the infrastructure, scaling, and the platform maintenance, while the deployment team focuses mainly on the application itself. And this is often useful for the teams that want to move quickly without managing their GPUs, model servers, or infrastructure operations directly. For example, a startup may prefer managed API because the team wants to focus on the product deployment or the development instead of the infrastructure management. while a regulated enterprise may still use the managed hosting but choose specific regions or the data boundaries to satisfy the compliance requirement. And another option is the self-hosting open weight models. Now, this gives much more control over privacy, customization, and the infrastructure decision. But it also introduces much more operational responsibility because the organizations now need to manage the infrastructure, GPUs, scaling, monitoring, and security themselves. So in Azure environment, different deployment approaches can support the different workload patterns. A standard pay-as-you-go deployment are useful for the variable workloads where the traffic changes over the time, while the provision capacity becomes useful when the organizations need predictable throughput and dedicated performance. Also, batch deployment can support offline workloads while the response do not need to return immediately, such as nightly report generation or the large document processing workflows. We can also think about the edge or the local deployment scenarios where the smaller models run closer to the user or inside the controlled environments. And this becomes useful for the disconnected environments, low latency application or sensitive workload where the data movement must remain limited. So when comparing the hosting options, we should not only compare the model names because the real decision also depend on the privacy, operational efforts, latency requirements, and the team's ability to manage the infrastructure over the time. And the managed hosting usually gives the speed and simplicity, while the self-hosting provides more control together with the more responsibility. Now let's move into the AI application architecture because in the production, a generative AI application is much more than just a model sitting behind a chat interface. Now, the model is important, but the real production solution is the complete architecture surrounding it. So a proper AI application needs a user interface, APIs, orchestration layer, retrieval system, prompt management, monitoring, and security all together. It may also need the identity systems, logging, and interactions with the external tools because the enterprise application must remain secure as well as traceable and reliable. For example, an enterprise knowledge assistant may allow the user to sign in through the Entra ID using a web application or Microsoft Teams interface, while behind the scenes, the system may use the document ingestion pipeline, vector indexes, prompt templates, retrieval system, and auditing logs together to produce the ground read responses with citation. And this is why we should not think of the model as the complete application, because the model is more like the reasoning engine, while the architecture around it provides the context, memory, control, and integration layers required for the production use. The architecture itself also changes depending on the use case. A simple content generation application may only need the prompt templates and a model deployment, while a support assistant may need RAG, ticketing integration, and tool execution. Now, a voice assistant may additionally require low latency streaming, real time orchestration, and escalation workflows. So, in Azure based environment, it often helps to think in the architectural layer. At the foundation level, we have governance and identity services like Entra ID, RBAC, and data governance control. Then we have the model layer, where the application interact with the AI models or the model routers. After that comes the grounding layer, where services like RAG, vector search, and MCP integrations provide the trusted knowledge and the external context. And above that sits the orchestration and the user interaction, where the workflows, agents, and the front-end applications come together. And finally, observability, monitoring, safety, and the cost optimization or the cost management wrap around the entire solution because the production system must remain measurable and manageable. And one of the biggest mistakes in AI application design is tightly coupling prompts, tools, business logic, and integration together in one place because this makes the system difficult to test, secure, and maintain. So, a cleaner architecture keeps the separation between the user experience, orchestration logic, and the execution layer so that the system can be easier to improve over the time. The simple way to remember AI application architecture is this. The model generates the answer, but the architecture makes the solution usable, secure, and production ready. Now let's move into LLM ops or the generative AI ops. So in traditional software project, we use the DevOps practices to manage the code, deployment, and operations. So in machine learning projects, we use ML ops to manage the training pipelines and the models. But generative AI introduces additional challenges because the important production components are not only always just code or the trained model anymore. They may include the prompt templates, retrieval indexes, evaluation dataset, or the multi-agent workflows. And this is where LLM ops becomes important because it represents the operational discipline required to run the generative AI systems reliably in the production. For example, if a team changes the system prompt for a support assistant, they should not deploy it directly without evaluation because even a small prompt modification may unexpectedly reduce answer quality or change the system behavior. Similarly, if the model version changes or the retrieval index gets updated, the organization must validate whether the AI system still behaves correctly and safely. And this becomes important because the generative AI outputs are probabilistic, which means small changes in prompts, models, or the retrieved data can create very different outcomes. So a prototype may work correctly during the demo, but the production system requires repeatability, governance, monitoring, and continuous evaluation. So a mature LLM ops setup usually includes the prompt versioning, response evaluation, latency monitoring, user feedback tracking, and the cost monitoring. Because even if the answers are good, the application may still fail from a business perspective if it becomes too slow or too expensive. Now, different tooling ecosystem supports these operational workflows. In Microsoft environment, Azure or the Microsoft Foundry, observability and Azure monitoring can help the tracing and monitoring, while the open source ecosystem may use tools like Langsmith, Langfuse, or Phoenix for debugging and evaluation workflows. But the tool use itself is not the most important part. The real value comes from the operational discipline because the prompts, retrieval logic, and the agents should be treated like the production components that are tested before the deployment and monitored after release and continuously improved using the feedback and the evaluation results. So the simplest way to think about the LLM ops is this. Building a working AI model is one challenge, but running a reliable AI application in the production requires the proper versioning, evaluation, monitoring, and operational maturity. Now let's talk about evaluation and benchmarking. Because in production AI system, it is not enough to simply say that the answer looks good enough. We need structured way to measure whether the system is actually performing correctly for the intended use case. Now, evaluation measures how well the AI application perform for our business scenario, while the benchmarking helps compare the models, prompt, or the architecture against each other. So, when a new models are released, providers often publish the benchmark scores, and that measures the capability across the reasoning, coding, science, mathematics, or the general problem solving tasks. Now, the benchmarks like MMLU Pro evaluate the broad reasoning and knowledge. GPQA Diamond focuses on the difficult science type questions or science style questions, and SWE Bench measures the coding performance using the real software engineer task. And there are also the other benchmarks like AIME or Frontier Math for advanced mathematics, OS World for computer use agents, and Chatbot Arena, where the humans compare the response from the different models directly. But the benchmark numbers alone should never decide which model is best because a model that performs extremely well on public tests may still perform poorly on a complete internal workflow or business document. For example, a support assistant may generate the fluent answer, but if it references the wrong policy document or retrieves the incorrect information, then the system is still unreliable, regardless of the benchmarking scores. And this is why the serious enterprise AI project should always create their own evaluation datasets using the real examples, expected answers, and the business specific valuation criteria. Then, whenever the prompts, retrieval settings, or the models change, the same evaluation set can be rerun so improvement become measurable instead of the opinion based. Now, evaluation should also continue after the deployment because the production feedback often reveals edge cases and the failure patterns that were not visible during the early testing. So, a strong AI system continuously learn from the failure and improve the evaluation coverage over the time. So, the simple way to remember this is that the benchmarking compares the model in general, while the evaluation measures whether the AI application actually works properly for the real users, real data, and the real business workflow. Now let's move into security because the generative AI security is much broader than simply protecting the model itself. So a production AI system may involve prompts, retrieval pipelines, external tools, APIs, and connected business system, which means the security surface becomes much larger than a normal chatbot application. And one major risk area is the prompt injection, where the malicious input attempts to manipulate the behavior of the model. For example, an untrusted document inside a RAG system may contain the hidden instructions telling the model to ignore the previous rules or expose the sensitive information. And if the application is not designed carefully, and the model may accidentally treat those instructions as the valid context, this type of attack is often called as the indirect prompt injection because the malicious instructions enters through the retrieval content rather than directly through the user prompt. Now, other tasks includes the data leakage, unsafe tool execution, excessive permissions, and uncontrolled agent behavior. So, if an agent accesses the database, email system, or deployment tools, then incorrect instructions or malicious inputs can create real operational impact. And this is why the production AI system requires the strong controls around the authentication, authorization, and the least privilege access, as well as the auditing logs. Now, input filtering and output filtering are also important because unsafe content should be detected before and after the model generates the response. Tool usage should be validated carefully, and in many enterprise environments, sensitive action may require the human approval before the execution. Now, RAG system also needs the proper access control because the retrieval layer should only expose the document that the user is authorized to access. And for the agentic systems, organization must additionally think about the tool misuse, repeated execution loops, and cost exhaustion risk. Because agents may repeatedly call the tools or expensive services if proper limits are not enforced. And this is why observability, rate limiting, logging, content safety checks, and the red teaming testing becomes essential part of the production AI security. Now, services like Azure AI Content Safety, Microsoft Defender for Cloud, and network isolation can help in the Azure environment. But the core security principles remains the same across all the platforms. So the main point here is that the AI security is a full architecture concern. We must secure the prompts, retrieval systems, tool integration, and the output together instead of only protecting the model endpoints. Now let's move into the responsible AI and the governance because the production AI system must not only work technically but also operate safely, fairly, and accountably. So responsible AI focuses on reducing the harm, explaining limitation, and ensuring the AI system behave appropriately within the organization and societal expectations. Governance provides the operational structure around this, including the approvals, risk reviews, monitoring, and the compliance processes. For example, if an AI application handles the customer data or supports sensitive workflows like healthcare, finance, or hiring, then the organization may require the privacy reviews, security assessment, and human approvals before the deployment. And this area is becoming increasingly important because global AI regulation is expanding. The frameworks like EU AI Act, NIST AI Act, and ISO compliances are helping the organization build more structured governance models for AI systems. But governance should not only be viewed as a compliance activity, because good governance actually helps the organization move safely from the experimentation into the production adoption. It ensures the sensitive data remains protected, risky use cases receive the appropriate oversight, and the user understand when they are interacting with the AI system. So in enterprise environment, governance may include the model approval, data classification policies, red teaming testing, access control, monitoring, and audit logging together as a part of the larger operational process. So the simplest way to think about this is the responsible AI defines how AI should be used safely, while the governance provides the control and operational structure that makes safe usage possible in the production system. And finally, let's talk about the cost optimization, because every architectural decision in the generative AI affect the operational cost. The model choice, token usage, retrieval size, and the number of the users all directly influence how expensive the application becomes. And one common mistake is sending too much unnecessary information to the model for every request. For example, if a support assistant sends the entire large document into the model for simple questions, then both the latency and the cost becomes unnecessarily high. So a better approach to use the RAG properly and retrieve only the most relevant sections needed for the current request. So the model routing also becomes important here, because smaller models can handle the simpler tasks while the stronger models are reserved for the complex reasoning workload. Another important thing is the prompt caching that can further reduce repeated costs when the same instructions or the context are reused frequently. Then comes the batch processing that can also reduce the operational cost for offline workloads where the real-time responses are unnecessary. Some organizations may additionally use the smaller models and quantized models or distilled models for narrow use cases where very large models are not required. But the cost optimization should not blindly reduce the quality, because the cheapest model is not always the best business choice. If the poor responses create the user frustration, rework, or operational issues, then the system may ultimately become more expensive overall. So the real goal is not minimizing the cost at any price. The goal is achieving the required quality, safety, and performance while keeping the system operational efficiency. Now let's connect this all together. So in this video, we moved beyond AI demos and explored what it takes to build the production-ready generative AI system. We started with the model routing and understood why different requests may require the different model. Then we discussed the deployment and the hosting approaches, including the managed API, provision capacity, and the self-hosted options. After that, we explored the AI application architecture and understood that the model is not only one part of a much larger production system. We also discussed LLM ops, evaluation, and the benchmarking, because production AI systems need monitoring, testing, and operational discipline. Then we explored the security, responsible AI, and governance, where the focus shifts towards the risk management, safety, and operational controls. And finally, we looked at the cost optimization and understood that the strong production system must balance the quality, performance, security, and the operational efficiency altogether. So the main message is simple. A successful demo is not the same as a successful production AI system. Real enterprise AI requires the architecture, governance, monitoring, security, and operational maturity from the beginning itself. So in the next video, we will continue building on the foundation and move into another important area of generative AI, where we'll connect these concepts with the practical solution design patterns and the real world implementation approaches. This is the final part of the Generative AI Foundation series. And in the previous videos, we slowly built the complete picture together. We started from the basics of how the models work, then understood how the RAG connects the model with the trusted knowledge, and after that, explored how the agents can use the tools to complete the real task. We also moved into production readiness, where we discussed the architecture, security, governance, and the operational practices. Now, in this final video, we are going to look at where the generative AI is heading next and why these changes matter for the system we will build in the coming years. And the AI space is evolving very quickly, and the way we want to design the application today may look very different even a few years down the line. And because these models are also becoming better at reasoning, they are processing much larger amount of information, and they are increasingly working with specialized systems instead of only text generators. So in this video, we'll discuss the reasoning model, long context models, mixture of expert architecture, remote coding agent, and the computer use before finally connecting everything together and understanding the broader future direction of the generative AI. Now, the goal of this video is simple. By the end, you should understand the major direction AI is moving towards, and why these changes matter, and how the architects and developers should prepare for the next stage of AI application. Now, let's start with the reasoning models. So, in the earlier videos, we discussed the large language models that can answer the questions, summarize information, and generate text. But the reasoning models go a step further, because instead of immediately generating a response, they spend more efforts working through the complex problem before producing the final answer. Now, this becomes useful for the tasks like the advanced coding, debugging, architecture analysis, planning, and the decision support, because these type of problems usually require the multiple step of reasoning instead of just quickly providing the output. So, while a lightweight model may work perfectly for summarizing a document or generating a simple response, a reasoning focused model may perform much better when the task involves analyzing a large cloud migration plan, comparing the multiple design approaches, identifying the operational risk, or working through a difficult coding issue where the system needs to think across several connected systems before responding. And in Microsoft and Azure environment, Azure OpenAI reasoning models support the scenarios like complex coding, workflow analysis, and the document comparison, while also allowing the reasoning efforts control so teams can balance the quality, latency, and token usage depending on the workload. OpenAI also exposes the reasoning efforts in the models like GPT 5.5, where lower reasoning efforts may optimize for speed and cost, while the higher effort may improve the quality for more difficult tasks. And outside the Microsoft ecosystem, Anthropic supports the extended or the adaptive thinking in the cloud models, while the Google Gemini models also support configurable thinking budgets for more advanced reasoning workflows. But one important thing to understand here is that the reasoning models are not automatically the best option for every request, because they usually take over, consume more tokens, and cost more, which means using them for the simple content writing or lightweight classification task doesn't make sense. And this is why the model routing becomes very important in the production system, because simple requests can go to a faster and the cheaper models, while more complex analysis can be routed to the strong reasoning models only when the deeper thinking is actually needed. So the simple way to think about the reasoning model is this: they are designed for the tasks that require the deeper analysis and the multi-step thinking. But in the production environment, they should be used carefully, because the stronger reasoning often comes together with the higher latency and the higher cost. Now let's move into the long context models. Earlier in the series, we discussed the context window, which is the amount of the information a model can process in a single request. But the long context models take this much further, because they can now work with extremely large inputs, sometimes hundreds of thousands or even the millions of tokens, depending on the platform and the model. Now, this becomes useful when working with a large contract, architectural documents, meeting transcripts, or the massive code repositories, because much more information can fit into one request without immediately needing the chunking or retrieval. So instead of splitting everything into many smaller sections, the model can sometimes analyze very large amount of information together in one interaction, which can make deep analysis more natural in a certain scenarios. Today, different platforms support the long context in different ways. OpenAI documents GPT 5.5 Pro with the context window of about 1 million tokens. So the Claude models support the long context workflows with very large windows, and Gemini models also focus heavily on the large context use cases. But this is also where we need to keep the message balanced, because the long context does not completely replace the RAG. Just because the model can accept the huge amount of text doesn't mean it will perfectly understand or use every detail inside the context, because the model may still miss the information while focusing on the wrong section, or become slower or more expensive when processing extremely large inputs. So a useful way to think about this is imagining someone reading a full 500-page book and then asking a very specific question, because even though all the information is technically available, finding the most relevant answer still depends on attention, structure, and clarity. And this is why the RAG still remains extremely valuable, especially when the organizations are working with a large collection of documents, access control, or continuous changing knowledge bases. Because RAG retrieves only the most relevant information from the current request, which often makes the system more efficient and more grounded. So, in the real architectures, the best solution is often not choosing between the long context or RAG alone, because strong systems usually combine long context, retrieval, and summarization depending on the scenario. Now, long context may work well for the deep, one-time analysis of a large document, while the RAG may work better for ongoing enterprise search across the thousands of documents where the knowledge changes happen continuously. So a simple way to remember this is that long context is very powerful capability, but it is still one tool among many. And good architecture is really about understanding where to use the long context, where to use the retrieval, and when to combine both of them together. Now let's talk about mixture of experts, often called as MOE. So this is an important architectural concept because it explains how some modern models can become extremely large without activating the entire model for every request. So in a traditional dense model, most of the model becomes active whenever it processes input. But in a mixture of expert architecture, the model contains the multiple specialized expert network internally, and only some of those experts become active for each token being processed. So a simple way to understand this is to imagine a company with many specialists, because the company may have the expert in coding, mathematics, language, and reasoning. But every meeting does not require every specialist to participate. If the task is related to coding, the coding expert becomes more relevant, while another specialist may become more useful when the task focuses on the reasoning or language understanding. So inside an MOE model, a routing system decides which expert should activate for each part of the input. And this allows the model to have very large overall capacity while using only a small subset of that capacity during the actual inference. And as a result, the system can become more efficient compared to activating every parameter for every request. And there are several modern open weight models use this approach, which are like DeepSeek V3 and Llama 4 and Mistral, because the idea is to give the model access to the broad expertise while still keeping inference more efficient than equally sized the dense model. But MOE also introduces complexity because the routing system must remain balanced, expert, and stay loaded correctly in the memory, and serving the infrastructure becomes harder to manage. And for most developers using the managed API, this complexity is hidden by the provider. But for the teams who are planning to self-host the open weight model, understanding MOE becomes useful because it affects the GPU memory usage, hardware sizing, and server architecture. So the simple way to think about the mixture of expert is this. Instead of activating the entire model for every token, the system dynamically select the most relevant expert, similarly to bringing the right specialist into the room for the right problem. Now let's talk about the future direction of the generative AI as a whole. So throughout this series, we have already seen how the AI has evolved from the simple text generation to much more advanced system that can reason, use different tools, process multimodal information, and support the real enterprise workflows. Now the future is moving towards a system that are more capable, more natural, and much more integrated into everyday business application, because the model will continue improving in the reasoning and planning multimodal capabilities, and this will become more common, and the agentic system will increasingly interact with tools, workflows, and enterprise platform directly. So instead of only answering the customer questions, a future enterprise assistant may retrieve the CRM information, analyze the support history, prepare a response for the human approval, and even trigger follow-up workflows automatically. While in the cloud operation, an AI system may investigate the alerts, review the documents, analyze logs, and compare the configuration changes and prepare the remediation recommendations before an engineer can even start troubleshooting manually. And this is where the AI starts becoming much more than just a chat interface, because gradually it has become part of the enterprise software stack itself. And another important direction we are seeing now is the remote control of the coding agents, because tools like the Codex are moving beyond the simple code generation and becoming long running development assistant that can inspect the repositories, analyze files, run commands, execute tests, and prepare the code changes over the time. Earlier, if you are running a coding assistant on your laptop, you usually had to stay in front of your same machine to guide the work, approve the commands, or the review output. But now the development environment may continue running on your laptop or the remote dev box while you monitor or control the work from the ChatGPT mobile app itself. So you may start a task from your desktop, walk away from your desk, and later use the phone to approve the next action, review the test result, check the differences, or continue guiding the coding assistant while the actual work is still happening inside the connected environment. Now, we are also seeing another related direction called as the computer use, where the AI can interact with the computers more like a human user by looking at the screen, understanding what is visible, moving the cursor, checking the buttons, and typing text. And this matters because many real world application or the business processes still happen inside the browser, dashboard, admin portals, and the desktop application, where the API may not always exist or may not expose everything needed for that task. So instead of only telling the user how to complete a task, so nowadays the AI system are able to open the application, move through the workflow, verify the result, and then return with a summary or recommendation automatically. So the bigger trend here is that the AI is becoming more operational and more connected to the real workflows, because it is no longer only generating answers inside the chat window. It is increasingly interacting with the coding environment, mobile devices, browsers, environment tools, enterprise tools, cloud platforms, and the business applications directly. So a developer may start a coding workflow on a laptop and continue managing it from a phone, while the business user may ask an AI assistant to analyze the dashboard or complete the repetitive workflow inside the enterprise system. But we should also keep the message realistic and balanced, because the successful AI adoption is not only about using the newest or the most powerful model. The same challenge we discussed throughout the series will continue to matter, including accuracy, trust, security, governance, privacy, and the operational cost. As the AI system gain access to more data and workflows, the architecture and governance become even more important, because these agents may have access to the files, repositories, and the production environment. And this is why the future of AI is not only about building the bigger models. It is about building better system around those models with the stronger controls, safe integration, approval workflows, and more reliable business operations. Now, over the time, AI will become cheaper, faster, and more accessible, which means the real challenge for organization will no longer be deciding whether the AI is possible, So instead, the important question will become where AI can create the reliable business value safely and responsibly. So the simple way to think about the future of generative AI is this. AI is gradually becoming the normal enterprise infrastructure, and the organization that succeed will not simply be the one using the best model or the latest model. They will be the one that combine the AI with the real business processes, strong architecture, governance and control, and secure integration across the organization. Now let's close this full generative AI foundation series together. Across this series, we started from the fundamental and slowly connected all the pieces together into one complete picture. We understood what generative AI is, how the model process information, how the prompt influence the behavior, and how the RAG helps connect the model with the trusted knowledge. Then we moved into multimodal AI, agents, production readiness, and finally the future direction of the AI system. So this series was never only about learning random AI terms or memorizing the concept individually, because the real goal was to understand how all of these pieces connect together inside the real application. So a model by itself is one part of the solution, because useful AI system also need the right prompts, trusted knowledge, proper architecture, evaluation, governance, observability, and security control around them. So the biggest message I want you to take from this full series is simple. Generative AI is no longer only about chatting with a model. It is becoming a practical engineering layer that can help the organization build smarter applications. And thanks for watching the full series, and I hope you find this useful.